Hello friends, hope you are having a fantastic day today. So in this section, we are going to do an entire course on backtracking. It is a very popular data structure and algorithm technique that can be used in all sorts of practical applications and tons of interview questions. In this section, we are going to learn that what is backtracking, when to use it, how to use it, what is the typical time and space complexity, what are the benefits, pros and cons of using and not using backtracking, and also how to identify backtracking kind of questions. And then we are going to see 10 most popular, most asked, most liked backtracking questions. So that is going to solidify your preparation completely. My expectation is that by the end of this course, you should become a pro in all sorts of backtracking and recursive kind of questions. So without any delay, let's get started. Now let's try to understand that what backtracking is. This is not any particular data structure, but rather this is a very important and very popular technique that we can use in all sorts of different scenarios. Let's say that you are at a current scenario where you are in a new city, and in this new city you are currently located at your home, and you don't have Google Maps at the moment, but you do know that somewhere around your house or around the block there is an ice cream shop that you are trying to find. So what you would do is, you know that currently outside of your home there are two different ways that go in each directions, and amongst these two different ways there are also two different possibilities that you can take in order to find the ice cream shop. And ice cream shop, let's say it lies over here and where you can find the ice cream, but you currently have four different options that you can choose from, where three does not lead to the ice cream. So what would be the logical step you would take? You would first of all start your iteration from your home, and you will pick any random guess. You know that at most you will have to make four different check out four different shops on four different places. So let's say that you decide to go down this path. Now once again at this path, once again you encounter two different possibilities. So once again, let's say that you decide to go down this path. Now going down this path, you realize that this is not an ice cream shop. So if this is not the ice cream shop, what should be your most immediate measure? So logical step would be to just do a backtrack operation back to the very previous point where you encountered the last possibility of different items that you could have explored, and once again explore those items as well. Once again, after exploring this, you realize that this is also not an ice cream shop. So once again you will go back, and after going back you notice that at this juncture you explored all the possibilities. So now once again you will go back to a point where you had some possibilities left. Now let's say that you come back to this moment, and once again you go back over here. Once again you have two possibilities. You coincidentally chooses this one, and this one turns out to be the ice cream shop, and you just found your ice cream. So that is awesome. Now what we did in all of these different jumps that we were taking on, these were actually the backtracking operations that we were doing. And what was our logic? It was quite straightforward, that whenever we are heading out and whenever we have to make any particular decision, we would just mark that what decision we took and what decision we are yet to take. We will take one of the decisions. Once again, if we encounter multiple decisions in such manner, we will pick any particular decision, and then let's say we did not find what we are looking for, we will go back to the very previous place where we still had some unexplored items that we did not take a look at, try to explore those possibilities, and then if we still don't find it, once again go back and repeat the same process. So you understood one thing very clearly, that we are actually repeating the same process we did at this point, and once again we would have repeated the same process we did over here, what we did, or if we had some possibility like this on this place as well. So logically we are just playing around with the same procedure with different inputs, and that is a very clear case of recursion. And you understood very correctly that backtracking and recursion go hand in hand. Many times when you are trying to realize that, hey, this is the problem where I'm dealing with a lot of different possibilities and I need to do some stuff differently, in that case you can come up with a backtracking solution that explores all the possibilities and all the subsets, all the permutations, combinations, you name it, whatever you want to say, all the different paths. And in that case, if you try to think of using recursion to solve the or implement that method, things would become much more sense. And this is the true power of backtracking, where it lies, because you can explore all sorts of different possibilities, no matter how many number of possibilities that you have to check. and you can find the answer you are looking for and keep on iterating with relatively slow amount or slow volume of code, and all everything can be done using recursion because you are just repeating the same process for different inputs. So this is the core concept of backtracking. So this is all that is needed to be done. It is a very simple uh, and very popular type of practice that can be used with all sorts of data structures. You can use it with arrays, you can use it with trees, you can use it with graphs, you can use it with strings. You can use essentially use backtracking with all the different kinds of data structures that are available, and it would work just perfectly fine. Now let's try to understand that what are the different benefits and what are the different cons of using or limitations of using backtracking. Number one benefit is that whenever you have to explore all the possibilities or all the subsets, all the permutations or everything, every single path that you have to take, backtracking is a really good and very profound tool in order to do this one. Next thing is it is relatively easy to understand and very simple to implement as well. And next thing is that it leads to solution no matter what. So you can guarantee to be finding the solution because you are essentially leaving no stone unturned. So there are some good benefits of using backtracking. The problem is with backtracking solution, typically notice that at every single moment, let's say that you have two choices to make and you keep on making those two choices, very soon the number of choices you have to make becomes exponentially higher, because at every single location you are updating or increasing in 2 to the power of n type of time complexity. And this can be one of the major drawback of using backtracking solution, because many times you are working with factorial or 2 to the power of n, or maybe like n cube, n square, sometimes of like these kinds of expensive uh, time and space complexities. And that's why you need to be very sure that whenever you are using a backtracking solution, that is like the only way that you are trying to use it. So if you are sure about it, then it becomes a really good and powerful tool. Because many times if the given problem is structured in a different manner, you can also try to think about some greedy approach or maybe some like shortcuts or binary search approach in order to make your backtracking more efficient. So just try to understand this point because this can come in handy in the future. And now I hope that my explanation made sense to you, that what backtracking is. You also understood that why we need to use backtracking with typically recursion. And now let's try to understand 10 different lead code interview problems that are like super popular, heavily asked, heavily depended, and a lot of people really like these questions. These questions has been asked in tons of different IT companies, like hundreds of times. So that's why I hope that after completing these 10 questions, you should be able to become a pro in backtracking. So without any delay, let's get started with those. So the lead code problem we are going to do today is called subsets, and we can see that this one is a medium problem and also a very well-liked problem on lead code. The statement is quite straightforward, that we are given an integer array called nums and we need to return all the possible subsets of this given array. So possible subsets means every single possible values or combination of values you can make out of the given array. So let's say that we are given an input element like this, and we are trying to determine that what are all the possible subsets that we are going to be able to make. So we know that for any given n value we can make 2 to the power n subsets. So in this case we should be able to make 4 different subsets. Let's understand that what these subsets are going to be. So first subset is going to be quite obvious, that is going to be an empty array, nothing more than that. And because that is a subset of this by default, because if we remove both of these values, still we have an empty array which we are able to generate using this. Next way, we can also generate values just 1. Same way we can also generate value just 2, and same way we can also generate value 1 and 2. So logically, using this logic, we should be able to try to understand that what is the way we can approach this question. And what I am suggesting is that this is nothing more than a decision making algorithm, where at every given step you are making the decision on whether you are going to include that element in your answer or you are not going to include that element in your answer, and based on that you should be able to come up with these 4 answers. So let me try to explain you my approach using this example, and then we will try to understand this for a bunch of different other examples. Let's say that currently we are given these two elements as part of the input. Now in order to generate the very first subset, we have two options, and let's say that we are also iterating over this given input array in this fashion. So the moment we iterate over this input array 1, the very first option we have is that we should we include this 1 in our answer, or should we not include 1 in our answer. So let's generate those subsets. So if we don't include 1, we come up with an empty list. If we decide to include 1, then also we are going to be able to generate a subset like this 1. Same way, next we have the option that after this 1, now the next element in the loop is 2. So once again we have the same option, that whether we should include this 2 in the answer or we should not include this 2 in the answer. So let's say that if we decide to include this 2 in the answer, then we are going to be dealing with values 1 and 2. Then once again we still have one more option, that is, because remember we are trying to build the subsets, so with every single value we iterate to the next, we are also going to calculate the possibility by removing the previous value. So let's say that we decide to remove this 1 completely, then also we still have one more option, that should we include this value number 2 inside the answer or not. So once again we will have one more subset like this, and then we have reached to the end of our loop, so we don't have any more options. So this logic gives us the correct answer of all the number of subsets that we can make, where what we did is at every given step we check that whether including that value or not including that value would result in some sort of subset, marking those subset in our answer array list we are going to create. And this answer array list is going to be list of list, because it's this array is also going to contain bunch of different array values, and where we are storing the value of every single result that we are calculating. So once again let me try to go and explain this for a broader scenario, the solution I'm proposing, and then it should make you absolutely clear on what is the approach we are suggesting. Basically at every single step we are going to make a decision to whether to include that element or not, and every single answer we generate, it is one of the subsets. So let's say at this very first position we have two options, whether to include 1 as the part of the answer or not to include 1. So let's see both possibilities. If we don't include 1, we have an empty list. If we include 1, we have one value, that is value number 1. Let's say we decide to go down the path of including value 1. Once again we have two possibilities, whether to include value 2 or whether not to include value 2. If we decide to include value 2, we are going to have 1 and 2. If we don't include value 2 and go to the next element, we are going to have value 1 and 3. And that's it. Now these are all the elements we have, so we won't be able to go any further, but we still have a decision to make, which is over here, that after this 1 2, do we need to include 3 or not include 3. So let's include 3. So that is going to be this decision 1 2 3. If we don't include 3, then it is just 1 and 2. That's it. Now once again, now we took care of all the possibilities with value number 1. Now let's try to work on value number 2. So once again we have the possibility of including 2 or not including 2. We already calculated if we don't include 2, then it is going to be an empty list. So let's include 2 now. So by doing that we are going to have one decision tree like 2. Now at this 2, once again we have two possibilities, include 3 or not to include 3. So let's decide to include 3. Then we are going to have value 1 2 and 3, and that's it. If we don't include 3, we already calculated that possibility over here. And last one is value number 3. So once again for this value number 3 we have two possibilities, whether to include this 1 and 2. We already calculated all of these by including 1 and including 2. If we don't include 1 and 2, then we only have one possibility, that is to have value number 3, and that's it. So these are at every single decision that we are able to generate, we are able to see that what are the values being generated by those decisions, and all of these are actually the answers or the subsets that we need to record. And that's it. This is the crux of the entire problem and the whole solution. So we can see that we are being able to generate in total these 8 values, and these 8 values are actually the answer we are looking for. Now let's try to think about that how did we generated this answer. The logic is quite simple. We do this recursively and using backtracking. And how do we do backtracking and recursively? Let's understand this with, first of all, what is the recursive pattern. So we know for recursion we need two items. First one is a base case and second one is a recursive function. So base case is quite obvious, that whether we have executed all the possibilities or we completed every single elements. So both of these base cases works perfectly fine, because at every step we would be able to generate an answer. So this is our recursive function, that whether we exhausted all the possibilities or we don't have any more elements that we need to traverse over. Now, what is the recursive function? It is also quite obvious that as long as any particular elements exist, then once again record both possibilities of including that value and not including that value as part of the answer. After doing that, once again do a recursive call back to the same function in order to check that if you include that value, then also what are the remaining values persisted. Call back the recursive function with those values. Once again, if you don't include that value, what are all the remaining values persisted? Once again do a callback operation, and if there are no other values left, then basically just do a return call. So this recursion would be able to generate the answer. Now, why do we need to do a backtracking? And that is also quite obvious, because what we are doing is that we are building a decision tree. So let's say that we are given this values 1, 2 and 3. So once again, we first check all the possibilities for this value number 1. So we check the value number 1, then we check value for 1, 2 and 1, 3, and once again we check for value 1, 2 and 3. And after, at this moment, we will once again have to go back and see that did we miss out any particular element or any particular possibility that we did not check. So far we did not, we checked all the possibility over here, we checked all the possibility over here. Once again we do a rollback. Once again we check, did we check all the possibilities? Yes, we did. So once again we do a backtracking and go to the next element and once again repeat the same operation. And that's why backtracking is the backbone of this problem, that allows us to solve this problem flawlessly and pretty smoothly. So this is how we are going to be able to use solve this problem using backtracking and recursion. And these two typically go in hand. Whenever you try to solve some problem using backtracking, most likely doing it recursively would make much more sense. We already know what is going to be the time complexity in this case. That is going to be big O of n multiplied by 2 to the power of n, because that is all the possibilities we will have to check. Now let's quickly see the coding solution. So coding solution is quite straightforward. First of all, we have our subsets class where we are receiving a nums as part of the input. Then we are generating a list of array list to store our result. And then we are going to call our recursive method that we have created, that is called generate subsets. Now we are passing in the current index, the starting index. Then we are passing in the nums array, and we are also passing in a variable to store our result. And also we are passing in a new array list, or the current array list that we are going to be creating, that we would be adding at every single subset iteration. Now let's see our helper method. So first of all, the moment we enter inside our subset, we are first of all going to add whatever the current array list that we have been able to generate it so far as part of our result as a new instance of the array list. And then we are going to have a for loop that is going to simply iterate over every single index position inside our nums array, where we are going to check for the following. First of all, we are going to add the current value as part of the current iteration that we are building, which would be added into the array list or into the result in the next iteration of the recursive call. Then once again, after adding the current value, we are once again going to call the current value as part of the result as part of the recursive call, and this is our recursive function. And after that, once that is done, we are going to be removing the current element in the next iteration. Why? Because let's say we are dealing with 5 elements, then at every given instance we need to remove 1 element after we are done iterating every single possibility at that value. So this is that step and that's it. So by the end of this array, every single value should be populated inside our result array list that we have been able to create it. And at the end of this recursive call is done, we are simply going to return that value. So let's try to run this code. Seems like our solution is working as expected. Let's submit this code. And our code runs 100% faster than all the other solutions, and also it is excellent in terms of memory utilization as well. So once again, the solution of this code is available on our GitHub repository, so you can go and check it out from there. Thank you. Now the lead code problem we are going to solve is called permutations, and we can see that this one is a medium problem and also an extremely well-like problem. The statement is quite straightforward, that we are given an integer array called nums of distinct integers, and we need to return all the possible permutations that we can make. And for good thing for us is that we can return answer in any order. So first let's try to understand this with few examples. Let's say that in the input we are only given one element, then we can only generate just one permutation. So this is what we need to return. But if we are given more than one element, let's say 1 and 2, then we can actually generate two permutations in this case. First permutation is going to be the same value as it is. In the second permutation, we are going to have the values being flipped around between 2 and 1. So these two are the permutations that we need to return. Let's take one more example. Suppose in the input we are given the values 1, 2 and 3. Then we can basically calculate that we should be able to make 6 permutations in this case. Why? Because for any particular given numbers, you can make n factorial permutation. So in this case we are given 3 elements, so 3 elements is going to be 1 multiplied by 2 multiplied by 3 as in 3 factorial. So in this case the answer is going to be 6. Now let's see that what are all these 6 elements are going to be. Well, so these are all the 6 permutations we can make. Now logically this is nothing more than a decision making element or decision making algorithm, because over here we can see that if we have to make permutation of this element, let's say that I have 3 blocks where I can fill in values. Now let's say for some reason I decide to put 3 in the first block, then I know that I still have 2 values where I need to fill out something, but the thing is I can only fill out between this value 1 and 2, not this value 3. So once again I can repeat the same process, and let's say randomly I decide to pick value number 1. So now for this last element I only have just one possibility, and that is to fill in this value number 2. And this, the moment it reaches to the length of this previous one, we can determine that this is one of the permutation that we can store as part of the answer. Now after storing this, we need to check that whether keeping this 3 over here at the beginning, are we leaving out or being done with all the permutations? No, there are still possibility of permutations left. Let's say that we decide to eliminate this value number 2 over here and this value number 1 over here. Now once again, keeping this 3 on this place, once again we have the option that instead of selecting 1, we can actually select 2 over here, then we will have 1 over here, and this would be a new permutation. So visually this is very simple to understand that how does this function, but the thing is implementing this is slightly tricky. So what I'm suggesting is that we actually use the same algorithm that we just saw, but we apply it using the logic and possibility and concept of backtracking. Plus on top of it, after using the backtracking, I also suggest that we use a recursive approach to recursively recall the same function with different inputs. And why am I suggesting this is because number one, we already know that we are repeating the same process. All we are doing it is that the input we are given, we are picking one value in, we are marking that particular value with one of the values, and for that let's say that over here we have 1. So once again now we have two possibilities. First possibility is that on this place, for the second place, we can fill in the value 2 or we can fill in the value 3. Once again, let's say if we decide to fill in value number 2, then we are only left with just one possibility for this last element, that is this value number 3, and this whole path defines one of the permutations. So this we will be able to mark as the answer, and then if we decide to go down this path, once again the values are going to be 1, 3 and 2. So this is going to be our second permutations, and once again we can mark this answer as well. So now let's say that what are the things we need to solve this problem and how we are actually going to be doing that. I just explained that we are going to be using backtracking plus recursion. So let's say that what do we need for our backtracking function? The idea is quite straightforward, that we will keep on going in one direction until we reach to the length of the given input. Once we reach to the length of the given input, we will mark that entire path in as part of the one of the answers, and we would put it into our list of lists that we have created to store our answers or results. Once doing that, the idea is to once again do a backtrack, and after doing the backtrack, once again see that what is the potentially different path that we could have taken, and once again once we reach to the answer, we basically store that answer. Now there are two critical parts in this case that we will have to consider. Number one thing is that we will need to know at some point that what are the values we have already calculated and what are the values we have not calculated so far. So what I'm suggesting is that let's say you decide to put 1 over here, then I would need some sort of way for my computer to tell me that this 1 is already part of the function. So for that, I'm suggesting to use a used array, or like array named use, and the moment we add any particular value inside the current consideration for our recursive function, we are going to mark this used function as true or false. So this would be my used array of Boolean values, and currently I would mark that this is true, which means I'm currently considering 1. Then once again, let's say that now I know that through my used array I only have 2 more possibilities left because this 1 has already been filled. So for the next element, I'm going to consider this value number 2, and once again I'm going to mark this value 2 as being used as one of the decisions. After doing that, once again I'm going to mark this value 3, and then I'm going to mark this 3 as being used. But the thing is, because I reached to the end of the list, so the moment I reach to the end of the list, I can mark this answer 1, 2 and 3, and after marking this answer, I can actually go back, and I can go back in time with my recursive function and say that over here, instead of using 2, now I have decided to take another path where I'm going to be considering 3 as part of the input. And in order to do this one, I will need to constantly update this used array. That is number one thing. Second thing is, in order to calculate this path, I will also need to have a current array or array list to store this path as well, that these are the values we are currently iterating. And the moment we identify that we have reached a new answer, then for the next iteration of the recursive call, I simply need to regenerate the entirely new array. So I know my solution might confuse you a bit, but let me just give you this with like using 2 examples. So let's first quickly take the example of simple 1 and 2 values. Okay, the logic is that we are going to have a recursive function that is going to store. So for the recursive function, I did not explain, but basically for the recursive function, we need 2 items. So we need a base case, and we need that what is going to be our recursive call. Base case is quite straightforward, that the moment we identify that our given current n, or the current length of the given input is equal to the original n of nums, then we have found the correct path. In this case, we would mark the current path inside the answer, and after marking that, we would basically return. So this is going to be our base case. Now for our recursive function, the idea is quite straightforward, that we are going to pick one element right now, and through that one element, we are going to be marking the used array for that particular element to be true. And then we are going to call the recursive function once again with the remaining portion, because we still haven't identified all the values. Once we identify all the possibilities and we receive an answer back, then we are going to eliminate the last element we had inside our recursive function to be turned out to be false, and keep on repeating that in order to calculate other possibilities. So let's first see for this example. The idea is that first of all, over here I have 2 possibility. Let's say I mark number 1 element as being used, and I have a current list where I'm going to store that what is the current path I'm taking. Okay, I took 1. Now I'm once again going to call for the next element. So now I call for the next element, that is obvious choice 2. So I mark 2, and now I know that my length of this current has reached to the n. So I'm going to mark this as part of the answer 1 and 2. After doing this, once again I'm going to do a backtrack call. During the backtrack call, I'm going to mark this 1 as not being used, and 2 as not being used, and then I'm going to be iterating over this given input in this fashion. So I already took care of this element, and now I'm going to start taking care of this element. So now I have my 2 as being used. Now I have my new current instance being created where I'm starting the path from 2, and I'm going to go down to the next path. So I only have one possibility, that is to add value number 1. So I'm going to add value number 1 over here, mark 1 as being used, and because this n is correct, so once again mark the another answer as 2 1, and now I have my answer that I was looking for. So after this, I realized that in my existing loop I already be done through all the elements inside the given input. So which means now whatever I have in the answer, I can simply return that. So now if you want, you can directly go to the coding approach if you already understood what I meant. If you didn't understood, then let me also do the same iteration for this path as well, and once again repeat the same procedure. So logic is, we are going to be iterating over every single element one by one. That is number one thing. Next thing is we are going to have our current list or the current values we are iterating over, and we are going to have our used array where we are going to be storing that which are the elements we have already used so far in the current iteration, and we are going to be updating the values one by one. So let's say that in the current path I add value number 1, so I'm starting the path from value number 1. After 1, I decide to add value number 2 as an input. So once again I do that, and after this 2 I add value number 3. So the moment I add value number 3, my length is equivalent. So I'm going to store the answer 1 2 3. After storing this, now once again I do a recursive call. So I basically break out, so which means I will have to remove the last element I added. Still keeping 1, I still have one more possibility that I haven't tested. So once again I'm going to mark 3 as being visited. So now I'm going to take one more path, and by the way, this is going to be a new instance where currently the nodes I have visited are 1 and 3, and next time I'm going to be visiting the value 2 because that element is left over here. So once again I'm going to be marking 2, and I'm going to have one more possibility, 1 3 and 2. Once again now I do a backtrack. So backtracking would make sure that I took care of 3 over here, I took care of 2 over here, and all of these things are done. So now my used array is being backtracked to all the way to the beginning. So now once again I'm going to repeating the same process, but now this time with value number 2, and keep on doing this recursively until we reach to this very last element 3, where we have all of the 6 possibilities calculated, and this is the whole solution. So now let's quickly see the coding solution, and that would make much more sense. Now first thing we are going to do is that we are going to create a new array list which is going to store our results. So now you can see that this one is an array list that stores different array list inside. Then we are going to initialize our used boolean array in order to keep track of that what are the current elements we have already used. And then we are going to have a helper method called backtrack, where as an input we are providing our result that we have calculated so far. Then we are going to have a new instance of an array list where we are going to be storing the current elements we are iterating over. Next, we are going to be passing in the given input nums, and lastly we are going to be passing in the new array used array that we have created. Now first we are going to be checking for the base case, that if the current size is equal to the length of the original given array, then we are going to add the results of the current array list inside the new instance of a new array list, and we are going to be doing a simple return. If that is not the case, then we have our for loop that we need to iterate over. So very first thing we are doing is that we are starting from the 0 and iterating I until we reach to the end of the array. Then we are first of all checking that if the given I value is not used, then we are going to be adding that value inside the current path that we are iterating over. So we added that. Then we are going to be marking that particular element as true inside our used array. And after that, we are going to be calling our backtrack method recursively, where once again, we are simply providing the results that we have calculated so far, the current path, which now contains a newly added element, and the nums input, and the used array that now contains that the current element is being used. And that's it. Basically, this should ensure that all the work gets through, and the moment the list size is correct, then we would start adding those values inside the result. But the thing is, after the backtrack call, we will also have to remove the lastly used elements. So we are going to be doing that, and we are also going to be removing that value, the very last value that we had in our current list. So we are always updating that in order to calculate new possibilities. And this is the whole solution. Now I know it's hard to visualize, but coding is very small, and also you can understand that how to generate it on a pen and paper. So you can just work around with different examples and it would make sense to you. Now let me quickly run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs super fast compared to all the other solutions, which means this is an excellent approach. Now I know using an extra used array might hamper with our space complexity, but this is still a much faster result. So now I will be posting the solution in our GitHub repository, so you can check it out from there. Thank you. Now we are going to be solving the problem subsets 2. Now this is very similar to our original subsets problem, but there is a slight difference. Now we can see that this one is a medium problem and also a very well-like problem. The problem statement is that we are once again given an integer array nums that may contain duplicates. So we need to return all the possible subsets. Plus we are told that the set must not contain duplicate subsets. So there is only just one tiny bit of difference. Now let's first understand that what does a different subset means. So let's say that we are given an input array like this, then the number of subsets it can contain is going to be 2 to the power of n. So where n is the given number of elements. So in this case we have 2 elements, so we can expect that 2 to the power 2, which means 4 subsets we should be able to create. And these 4 subsets are going to be an empty list, a subset only containing value number 1, a subset only containing value number 2, and a subset containing value number 1 and 2. That's it. So this is the whole solution. But the thing is, I know we just solved this problem in like our subsets problem, so if you want you can check it out from there. The thing is, in this case, the only difference is that let's say that we are given a value like this where the input may contain duplicates. Then this changes our equation a bit, because in this case we need to only return the unique subsets. So in this case, if we want to create the number of subsets, definitely we can create 2 to the power of n subsets. The issue is that we can create a subset, we can create like an empty subset, then we can create a subset with just one. But once again, if we try to create a subset with this 2, let's say, then we can also create a subset like this 2. And if we were to put both of these in the answer, then there would be duplicated entries. So we only need to just pick one. So that is number one thing. There can be one more duplicate in this case, and that duplicate could be that we can create a subset like this, value 1 and 2. And we can also create a subset like this where value is 1 and 2. So if such kind of situation occurs, then we need to take care of that scenario. So basically making sure that whenever we have duplicated entries, we just have to keep them aside or not consider them for the current part of the subsets. Now we all know that what was the strategy we used in order to calculate the subsets. Let's say that we only have just 2 values given and we are trying to generate the subsets. Logic is quite straightforward. We are going to be using the backtracking. On top of it, we are going to be using recursion. Now what is going to be logic for our backtracking? That while after calculating every single path for every possible subset, then we are going to be doing a backtracking and once again repeating the same operation. What do I mean by that? Let me just explain. So first of all, we are at the empty list position. Now over here we have the possibility to include this value 1 or not to include this value 1. Same way we have the possibility to include this value 2 or not to include this value 2. Let's say that we decide that we are not going to include both of these 1 and 2. So in this case, we can create a subset like this, like an empty list, and we will mark this as part of the answer. So let's say that this blue line indicates that we already marked it as the answer. Now, once again, after marking this answer, we still somehow needs to go back and revert our operation. So in the previous choice, we decided that we are not going to select this value number 1, but now let's say that we do decide to go ahead to select this value number 1. So once again, we can create a subset where we are only selecting the value number 1. So once again, this is also part of the answer. So I'm marking it with a blue line. But after doing this, once again we will have to do a backtrack and see all the possibility. So we already exhausted all the possibility of selecting one and not selecting one. But the thing is, we haven't exhausted all the possibility of selecting two and not selecting two along with this one. So let's say that along with this one, we have the possibility that whether we select two or not select two. So we not selecting two, we already calculated. But now we are calculating one more possibility where we are selecting two. So we have values like 1 and 2. Okay. After doing this, we can do a backtrack. We check all the possibility at one. Once again, we check everything so far. The thing is, we haven't checked the possibility of only considering two. So once again, we are simply going to be considering two, and this is going to be our backtracking mechanism. On top of it, this is also going to be our recursive function that I just explained, where for the recursion we need two items. We need a base case and we need a recursive function. So for the base case, it's quite straightforward that whenever we create or we make any single decision, we simply add it to the answer, and this is our base case. After this, for the recursion, we go back to the next recursive call with that selected value or not selected value, and once again repeat the same process for the next upcoming remaining elements inside the array. So this already makes sense. We already do this. But the only issue in this case is that we simply don't want to consider, let's say that we are given values 1, 2 and 2. So now in this case, once I'm making the decision, let's say I put down the empty array, then I put down a list with 1, right? Now at this 1, I have two possibilities. First possibility is that I'm going to be considering this 2, and second possibility is I'm not going to be considering this 2. So let's say I decide to consider this 2. Then I should be able to create an input array like this, or like a new subset like this. Once again, let's say that I go to and let's, for a simplicity, let's assume that this value is currently 3, okay, not 2. So if this value is 3, then I create one possibility where I'm considering 2. I can also create one more possibility where I'm not considering 2, which means there can be a subset like this 1, 3. But in this case, rather than this value being 3, this value is also 2. So it's the same value. So if I try to do this possibility in this case, then I'm just stuck. I'm left with only this value. So what I can simply do is that I can take the given input. Let's say the given input array is like this, but it right now it is already sorted, but it is possible that this may not be sorted. We could have given values like this. So once again, if we want to do the solution, what I'm suggesting is that whatever values we are given, we simply sort those values. So let's say we get a nice looking values like this. After sorting, all we simply do is we check that at any given moment, whenever we calculated a possibility with this 2, now we are trying to calculate another possibility. We just check that the current element we are considering for the possibility, if that element is same as the previous element, then we just don't consider that possibility. That's it. This is the whole solution. So now what would happen in this case? We will have an empty list. We will have value with 1. Now we will have one more subset with 1, 2. Now after this 1, 2, we still have two possibility whether to include this 2 or not to include 2. So let's say that we decide to include 2. So then we still have one more subset like this. So we also consider that. After this one, we are doing our backtracking by removing the last element added. We do the backtrack. We don't need to calculate this one because we already know that it's the same element. We go back to 1. We check all the possibilities with this 1. So now we are at this position number 2. So we decide to include 2 only. This is a new subset. We add it to the answer. Now after at this 2, we have the option that whether do we need to add this value or not to add this value. So this value is quite straightforward. It's 2, 2. It's a new subset. So we haven't calculated that. So we can simply add this one. Now after calculating this, once again we do a backtrack. Now at this backtracking location, now our time is to move to the next element and not consider this one. But once again, while making a decision for this one, we check that whether it matches the previous element. Yes, it matches the previous element. If it matches the previous element, what is the point of considering this for the subset? So we are not going to do that. And that's it. This is the whole solution. And if you see the coded approach, it would make much more sense. Plus you already know that how does the calculating subsets work, because we already saw that in the past, that the whole explanation and the whole 9 yards. I just re-explained the whole thing, and I also explained that why we are adding this tiny logic to our already beautiful solution. Now let's quickly see the coding approach. So very first thing we are doing is creating a new array list where we are going to be storing the results. Then we are simply sorting the given input array. And then we are calling our backtrack recursive helper method where we are passing in the new result where we are going to be storing the array list of lists, and we are passing in the new instance of the array list to store the current list that we are iterating over. Then we are going to be passing in the given input nums, and we are also going to be passing in the starting index where we are looking at. So initially we are starting from the index 0. So we are just going to pass in 0. Now let's see our helper recursive method. First thing we are doing is whatever value we have in the current list, we are adding it into the answer. So during the very first call, we are adding just an empty list into the answer as well. Next, we are running a for loop from the start to the end of the given array. Plus, we are just checking for a very simple condition that if the given input I is greater than start and the current element is equal to the previous element, if this is the case, we simply continue. If this is not the case, then we simply add the value to our current array list. Then once again we call our recursive function. After the call comes back from the recursive function, we remove the very last element added inside the current array list, and then we repeat the same process until we are done with the entire for loop. And this should populate our results completely. So now let's try to run this code. Seems like our solution is working as expected. Let's submit this code. And our code runs beautifully, faster than all the other solutions, and also best in terms of space complexity. So once again, the solution is present at our GitHub repository, so feel free to go ahead and check it out. Till then, thank you. Hello friends, hope you are having a fantastic day today. So in this video, we are going to do a very popular lead code problem that is going to be pretty nostalgic for a lot of people. So without any delay, let's get started. The title of this problem is called letter combination of a phone number, and now many of the iPhone users won't know it. But in the past, phone actually did used to look like this, where if you have to type any messages, you will need to do it according to the keys that are present over here with the corresponding numbers. And people were so good that they were able to do it without even looking at it. But anyways, now coming back to the question, this is a lead code medium problem and also an extremely well-liked problem on lead code. Also has been asked at tons of popular companies. So let's see that what does the problem statement ask us to do. Basically, we are given a string containing digits from 2 to 9, because notice that in this problem, we are only given the characters from A to Z present between the letters 2 to 9. Now, inclusive. Now we need to return all the possible letter combinations based on the given digit numbers, and that it can be represented. For our convenience, we can return them in any order. So let's try to understand this with a couple of examples. Suppose we are given as an input just character number 4. So how many characters does this character number 4 can represent? Well, only 3 characters. So if we have to return this, the answer is going to be G, H and I as the answer that we need to return. But let's assume that instead of that, we are given the input as like 4 and 6. Then what should be the answer? So we know that 4 can represent G, H and I, and 6 can represent M, N and O. So the answer is going to be the combination of both of this GHI and MNO. So the answer would look something like, where you can see that currently we have 9 entries and they are combination of all the characters from these two entities, and that's what we need to return. So this is the whole problem statement. So let's try to see that what is the approach we can take to solve this problem. Now, number one thing is that currently we are only given characters between 2 to 9 as an input and nothing else. So first thing we need to do is that we will have to create a mapping so that based on any given input location, we can actually identify that if the character 2 is given, we know that it can only have the possibility of storing ABC. Same way, if character number 9 is given, then it only has the possibility to store 4 characters W, X, Y and Z. And same way, we can store this in any such fashion so that this lookup needs to happen in big O of one time. So we actually have two options to do that. Number one option is that we can actually create a hash map, and inside the hash map we can store all the entities, and based on the key we can mark as the digits, and their subsequent values we can mark all of the entries. So that is option number one. This will yield in big O of 1 time complexity whenever we have to do the lookup. Second option is, since we know for sure that we are only dealing with characters between 2 to 9, nothing more, we can also create an array, and inside the array, based on the index positions, we can store the values. So let's assume that because in the array we have values like 0, 1 and then 2 and all, so on and so forth. So for 0 and 1 we can store as an empty strings, because anyways they are not going to be part of our inputs, and starting from position number 2 we can start storing values as A, B, C and stuff like that. Now this is only for our convenience purposes, so that we can quickly look up what element we are trying to find. Now this is the pre-work that needs to be done in the solution so that we can do it in the efficient manner. Now let's see that what is going to be the optimal approach to solve this problem. Suppose as an input we are given the characters 2 and 3 that we need to return. Now we know that 2 is represented by A, B, C and 3 has been represented by D, E, F. That we actually take this given input 2 and 3, then we break this input based on all the digits it currently has. So first we get the digit 2. For digit 2, whatever the characters that it can represent, we create 3 decisions trees based on that. So currently it can represent A, B and C. So we create 3 separate decisions tree. And now, since this is not the answer, because we need to return the combination or the potential combinations that can be there. So this is just a part of the answer that we have created so far. But now we will have to complete the combination portion. So in order to do that, the number one thing we will need to do is to keep track that how many number of characters are currently present, or how many number of digits are present and how many are pending. So now 3 is pending. So we will append 3 with each of these decisions trees, and we know that 3 is currently represented by these 3 values. So once again, for each one of them, we are going to have 3 separate decisions tree being made. Notice that currently at this very first location 2, we only had 1 entry per character inside our representation. But the thing is, in the input we were given 2, 3, 23, which means we were dealing with 2 character letter. But in the problem, we are only at half of the step, where we only have just 2, which means after creating this possibility, we still have to wait to add the values to the answer until we find this path where now the index position matches the total number of inputs that we are given. The moment this condition matches, we will need to add it to our answer list. So because over here we only had 1 characters, but now we had 2 characters, and even in the input we were dealing with 2 characters, we are going to add DA or AD in the answer. Same way AE is going to be part of the answer. Same way AF is going to be part of the answer. And the good thing about this is, because this is same operation being done multiple times, so we can actually keep on doing this. The moment we find out that this is one of the potential pair that we have already added to our answer, we can actually backtrack to see if A still has any more values that it needs to add to the answer. And yes, AE still needs to be added. So we will add AE. Once again, we will backtrack to A, and once again this AF needs to be added. So we will do that. Once again, we would backtrack to 2. Now we have completed all the path with A. So we will repeat the same process with B. And this is the whole answer we need to return. Now I know what I just explained might have confused you a bit. So that's why when we do go into the coding section, I will explain the whole thing in much more clarity. But this is the whole approach. Basically, we are simply using recursion and backtracking to solve this problem, because repeatedly we are doing the same operation. And we know that for this, we need to have an terminating case. So terminating case would be that the moment we identify that one path or one combination contains the same number of characters as the number of input that is given or the index values, then we need to add it to the answer and once again do the backtrack, keep on repeating the same process until we have exhausted all the possibility, and whatever the answer we found, we need to return that. Okay, so what is going to be the time and space complexity in this case? The time complexity is only going to be the number of potential combinations that can be made, which means the number of characters that are given. So let's assume that this currently has 3 times 3 6 characters. So whatever the value is, so we need to do square of the number of given input for every single digit. So in total, it is going to be the number of combinations that are currently present. That is going to be the time complexity. For the space complexity, because we will have to create another array that contains all the mapping from the characters 2 to 9, we will have to store that, but that is going to be limited in scope. So instead of calling this as big O of n, we can actually treat it as big O of 1, because the space complexity is not going to change. So now let's see the coding solution. Okay, so first of all, we are going to initialize our string array, where we are going to mark first couple of entries as blank, and then we are going to mark all the values. So this is going to allow us to iterate over all the digits to the letters. And then let's start our code actually for the problem statement for this method letter combination, where we need to return a list of strings as the answer. So first we are going to initialize a combination string that we are going to return as the answer, and this is going to be the blank array list so far. Now first we are going to check for an edge case, that if the given number of digits is equal to null or digit.length is equal to 0, then we simply need to return combinations. If that is not the case, we are going to call our backtrack method, and we are number one thing, we are passing this list that we have created. We are also passing the input digits that we have received. We are passing an empty string that is going to be considered as the current combination that we have so far, and we are passing in 0 as the current index values that we have processed so far. Okay, now let's see this backtrack method. How does it work? So number one thing we are checking is that if this given current index location, if that is equal to the digit length, which means we have an answer that we need to add to our current combination. So we are going to add all the answer that we have found in the current combination to our combinations array list that we have created. If that is not the case, we are first of all going to differentiate the letters for every single index position. So let's say in the input we are given value number 2, then we would have ABC as the letters passed on, and then we are going to run a for loop across every single letter. But now this time we are recursively going to call back the method backtrack. We are passing in the same combination, same digits, but for the current combination, we have added the current combination plus the current letter we are working on. On top of it, we have also updated the number of increased value, index value. So if in the previous iteration, if we would have passed in value number 2, in the next iteration, we would have passed in value number 3. And that's how we will be able to start storing all the combinations in the current combination array string that we have created. And this is it. So let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs pretty efficiently compared to a lot of other solutions, which is awesome. By the way, you can always find this coding solution in the GitHub repository we have, and the link is in the description, so you can check it out from there. Thank you. Hello friends, we are still not employed by a FANG company, so let's not stop lead coding till we get there. Today we are going to do a very important lead code problem, and I have provided the introduction of what are the things to expect from this video. We are going to solve the combination sum problem, and first of all I'll be showing that what are the top companies that have recently asked this question from Lead Code Premium. We'll understand the problem statement. We'll also find the optimal solution, and we will also determine that what would be the intuition behind it. We will create an example and we'll walk through it, and at the end I'm going to write a Java code. I'm going to explain it thoroughly, that how we come up to it, and also we would be explaining the time and space complexity. So first of all, these are the top companies that have asked this problem recently, and if we see from past 6 months to a year, it's eBay, Google, Goldman Sachs, and these companies. And in pretty recently, Amazon has asked this question 20 times in its interviews. Facebook has asked this question 18 times in its interviews. So I highly suggest you to take a look at this problem, understand it completely, and then practice it as much as you can. This is a medium problem, and we are given a distinct integer called candidates, and we are also given a target integer, and we need to return all the unique combinations of candidates where we can reach up to the target value. Now this is a little bit tricky part to find all the unique combinations for this target candidate, because let's try to understand this with an example. So over here we are given the candidates as 2, 3, 6 and 7, and we need to reach the value number 7. So we can clearly see that 7 is already present over here, so we can return this one. The thing is, we need to return all the unique combinations. So one unique combination is 7, second unique combination, and also one more thing, we can use the same number from the candidate unlimited times. So if we apply this theory, then we can find another value that can reach to the sum of 7, then that would be 2 plus 2 plus 3. If we do that, this also sums up to 7. So we need to return a list where the two values are 2, 2 and 3, and the second element is just 7, and this would be our solution for this given problem. Okay, let's try to understand this problem with a custom example. And it is really important to create your own custom examples, because it shows that you have the ability to think outside of the box, and you can create test cases on your own. It is a really important skill to have for any engineer, and especially FANG engineers. So we are given three candidates, 2, 5 and 6, and we need to see that what are all the combinations we can get out of these candidates to achieve the target value 8. Now just by looking at it, we know that the two combinations we can create is 2, 2, 2, 2. This is one combination, and the second combination we can create is 2, 6, and this would be our answer. The thing is, let's see that what would be the most basic solution we can come up with, and what would be the intuition behind it, and based on that we would be able to create an algorithm that would solve this problem. So initially we are at this position 0. Now at this position 0 we have three possibilities from which direction we can go. We can either go to this value number 2, we can go to the value number 5, or we can go to the value number 6, because these are the three candidates that we are given. And also we should not forget that the target value we want to achieve is 8. Okay, so keeping this in mind, we need to go and pick a side where we need to go further and keep going. So again, let's just go on one direction for all the cases we can. So over here we are at 2. Now remember that we can use same element infinite times, which means that there can be one possibility as 2, 2, of course. There can also be one possibility as 2, 2, 2, of course. The thing is, notice that we need to put a constraint for the number of decisions we are making, and the constraint is that if at any point the direction where we are fetching all the candidates, if the sum of those can either be less than target, they can either be equal to target, or they can be greater than target. These are the three possibilities we can have. If it is less than target, which means that there is still room for us to find the potential combination, which means we can keep further going on that direction. If we are already at value number 8 or value whatever target we are, we can directly put this value in the result. But if we and which means that we have found the combination, so there is no point in going further after we have already found the combination, because all the elements, they are only going to add up to whatever combination we have, which means that we won't be able to find another combination with the same numbers that were used to achieve this equal to. And the third option is that the value could be greater than 8. If it is greater than 8, why are we keep on going or to do more iterations and putting more strain in our computer? There is no point in doing it, because we could have infinite options, and if we do it, this would be like the best way to deplete the resources of our company. So we don't want to do that. So now, since we have kept these things in our mind, now let's see that how can we use them over here. So far the sum we have found up until this point is only 2. But the thing is, over here we have 2 candidates, and the sum we have found so far is 4, which is still less than 8. This is 6, again still less than 8. Now over here we can have one more possibility as 2, 2, 2 and 2. And if we do the sum of this, this is 8, which means that this is actually equal to whatever the target value we had. So we can add this to our result combination. We would have that we have already find one value in our result, and we will just add it as 2 2 2 2. This is one combination that we have found so far. The thing is, we are not done yet because we still have other candidates that we need to look at, and we need to check the possibilities. But the thing is, we have concluded at least one thing so far, and that thing is we can't go further down on this path because all the values would be greater than 8, and which is not what we want. So the only way we can go is actually we can go back and see that have we missed out on any combination. So over here, the next possibility we can get is we have already used 2 as our candidate for this value 2 2 2. So the next possibility we can have over here is it could be 2 2 2 and 5, or it can be 2 2 2 and 6. So let's do sum of all the combinations. So some of these combinations would be 11, and some of these combinations would be 12. Notice that both are actually greater than the value of our target, which means that we can't go further down at any of these positions, and we have exhausted all the possibilities up until this point. So since we have already exhausted the possibilities up until this point, the only way we can go is we can go back. At this position 2, we have exhausted all the possibilities there can have. One, we found the answer, and the other two we found that it cannot be part of the combination, which means that we have already exhausted all the possibilities for this value 2 to 2 as well, which means that we can't go down, but we can go up. So over here, have we exhausted all the possibilities so far? No, there are still room, there are still other possibilities that we can check. So let's do that. So one possibility we can have over here is 2 2 2, which we already checked. The next possibility could be 2 2 5, and the next possibility would be 2 2 6. So sum of these values is actually 9, and some of these values is actually 10. Again, both are greater than whatever the target value we had, which means that we cannot go down. So we will go back. We went back. Over here we check that we went through all the possibilities, which means that we are done over here. So we can't go down any further on this path, but we can go up. So if we go up, we ask ourselves a question that have we explored all the possibilities at this position? No. The possibilities we could have is 2 5 2 6. So let's take this value first. So at 2 5, the current sum we have is 7. 7 is less than whatever value we have as our target, which means that we still have possibilities. The possibilities we can have is 2 5 5 or 2 5 6. Notice that over here we only had two possibilities where we can calculate it from. We did not had the possibility of 2 2 5. Why? Because we already calculated it for this portion over here. Remember, in the previous iteration we already calculated for this scenario, which also shows one very important property, and their property is that out of our candidates, whatever the candidates we are given, if we are at any particular position or any combination of positions, so whatever value we have as last, we can only use that multiple times, or we can use the values that come after it. We cannot go backwards because we have already exhausted those possibilities in an iteration before this, as I showed you earlier, that this we have already explored over here, and this 2 to the 5 2 5 we are exploring at this position 2, which means that the only combinations we can make up after this point is either 2 5 5 5 something blah blah blah, or 2 5 6 6 6 something like this, but we can't make like 2 2 2 5 because we already checked that over here. So, and this is a very important property that we are going to use. Okay, at this point the sum we can have is 12, which is greater than 8. so we can terminate over here. We can't go down any further. And over here the sum would be 13. Again we can terminate over here. We can't go down, which means we have to go back. So we come back at 2 5. We say that okay, we have explored all the possibilities over here. We go back to value number 2. Now the thing is, at value number 2, have we explored all the possibilities? No, there is still one possibility pending, which is 2 6. So at 2 6, this value, the sum would be 8. Again, this is really critical because we have found a pair that equals to whatever target value we had, which means that we will add this combination to our result list. So over here we will add another entry 2 6, and after adding this, we have explored all the possibilities after this point, which means that we would go back. Now at this position 2, we have explored all the possibilities it could have, and because we have explored it, we will again go back to our 0th position. The thing is, we are still at 0th position, so can we stop now? No, we can't stop because we still have a whole lot of possibilities that we haven't touched so far. Because remember, over here we still have this 5 and 6 pending. So let's see that what could be the possibilities over here. Now at 5, again we can only have two possibilities. As explained earlier, we could have either 5 5 or we could have 5 6. So let's do the sum of these values. So 5 5, the sum is actually 10, and 5 6, the sum is 11. Both are greater than 8, which means that we can terminate over here. So that concludes that at this position 5 we ran out of the possibilities. We went up. At this position we are done. So again we go back. At 0th position. We check that do we have any other options where we can explore, and yes, currently we are at value number 6. So 6 is again less than our target 8, so we can go further from 6. The thing is, at 6 we can only do 6 6. We can't do any other combination because those we have already checked so far, which means that 6 6, the value is 12. So 12 is already greater than 8, which means that we can't go further from this, which means we can't go further. We go back. At 6 we see that have we explored all the possibilities? Yes, we have explored all the possibilities, which means again we go back to this position 0. So at this position 0, we check that now have we explored all the possibilities? Yes, initially we check all the possibilities for the value 2, again we check for value 5, and again we check for value number 6, which means that even at 0th position we are done. So our base case has satisfied. Now whatever we have stored in our result result list so far, we can simply return this, and this would be our final solution. And this is actually the optimal solution that we can achieve. Notice over here that we are doing lot of repetitive work. At any position we were calculating the different possibilities we can have. We were picking a possibility, we are exploring in that direction, depth first search. We kept on exploring. Once we found a terminating case, we would go back to a point where we can still explore for more possibilities. Over here again we would further go down to additional possibilities. We would find a terminating case, again we would come back, and eventually we would come back to the 0th position from where we started, and after the calculation we will return our result. So this, where at any point we are coming back from where we originally started. This is actually called backtracking. This is a really important concept in computer programming, and I just showed you that how can we use it, and that is why, because this concept is really important, it has a lot of very practical applications, and that's why you see that why all those big companies like Google, Facebook, Amazon, Goldman Sachs, they were interested in asking this question to their candidates, because they want to know that are you familiarized with very important things that are really critical, and can you go down that path. And yeah, so since we have found our optimal solution, I did not mention explicitly that I was showing you the optimal solution, but the thing is, I told you that this is the intuition behind it, and once we knew the intuition, we just need to find a way to implement it in computer programming. The way to implement this, you must have guessed it correctly, that we were doing so much repetitive work again and again, and we were using it somewhere, and we had some terminating conditions that either if the value is equal to or greater than our target, we would terminate, which means that we were using recursion at its best over here. So yeah, this is basically our solution. So let's calculate the time and space complexity. That time complexity for this one would be big O of n to the power t. Now first let's determine that what this n and t means. N is actually the number of candidates and the least value for this one, and t is actually the total amount, because imagine that what could be the longest sequence we can have at any given position. Well, suppose our target value is 8 and our candidate is 1, which means that we would do 1 plus 1 plus 1 up until 8 times till we get the value 8, which means that we need to go in one direction 8 times, and at any position we can have multiple options or we can make multiple decisions, and from further down we can go ahead, which means that we need to do this work n to the power t times until we find the solution. So that's why this is the time complexity. So first of all, we'll create our result list, and now we'll create a list to store the current combination. Okay, now we'll create a backtrack method, and in this would be our recursive method. So initially we are going to provide the target result combination 0 as the starting point and the candidates array, and after whatever the result we get back from that recursive call, we simply need to return whatever we find in this result list. So let's create the recursion method. Okay, so first of all we are going to create the terminating cases. So if target is equal to 0, which means that we have find a combination that sums up to the target value, so we can just simply return it to we can simply add the combination to our result. If this is not the case, we need to return we need to check that whether the target is less than 0, which means that we have already surpassed our target and we need to break, so we can just return null. If both cases are not true, which means we still need to look for our combination. So we'll start by checking in our combination from the position start, and we'll go until we still have candidates. Now inside the loop, first of all we will add whatever candidate we are currently looking for in our combination list. Okay, after that we can do our recursive call, and as a target we will have target minus whatever candidate value we found. And start would be ith position, And I think that would be it. Yeah, one more thing, we will have to remove the entry from our combination list, because we will be doing backtracking when we move towards the next value. And I think this would be it. Let's try to run the code. This should have worked, but I don't know why it's not working, so we'll just enter the value manually. Oh, it should be candidates. Okay, our solution seems to be working. Let's try to submit the code. And yeah, our solution works perfectly fine. And now we are going to be doing an awesome lead code problem that is called combination sum 2. This is the subsequent question to our original combination sum problem with some slight tweaks. Now we can see that this one is a lead code medium problem, but in my opinion this can be categorized as hard problem sometimes as well, because combination sum in itself is slightly tricky to understand. And we can see that this one is a very popular lead code problem, also being asked at tons of companies. Basically we are given a collection of numbers called candidates, and we are given a target number. Now we need to find all the unique combinations in the given input array such that the sum of those values is equivalent to the target value. There can be more than one results, so we need to consider all of them. Now we are told that each number in candidates may only be used once in the combination, and we need to make sure that the given solution set must not contain any duplicate combinations. Okay, so now let's first try to understand this with an example. We are given this candidate array and we are given the target value to be 5. Now next thing is that we need to generate the unique sets. Now let's see that what are all the combinations that can generate this value 5. We can see that we have value 4 and we have value 1. So 4 and 1 is a combination that can sum up to value number 5. So that this can be one of the potential answers. Next one is we have value 2, 1 and 2. So once again we can generate value like this, and this can also be an answer. Next value is that we can do 3 to 2. This is also one of the subset that can generate the answer. But now there is one problem over here. We also have this 3 that we can utilize with this 2 to once again generate the target value 5. The thing is that value is also going to be 3 2, which we have already entered in our result. So we should not be reusing the same set in our results, because we need to make sure that this answer becomes unique. So if we, by considering these elements, we can only generate these 3 values or these 3 sets that combination to the total value 5. So we need to understand that this is how we need to solve the problem. So now let's try to see that what could be the potential solution over here. Now logically, the very first thing that it would make sense for us to do is that instead of treating all of these weird values side by side randomly, it would make much more sense to, number one, sort the given input array. Why am I suggesting to sorting the given input array? That has two reasons. Number one reason is that let's say that we have some values like let's say 10 and 15 and then so on and so forth, like 100 other values, okay? And we are given the target value to be 5. So the moment we reach to a value 10, then why do we even have to check possibility for all of these 100 values if we have already sorted the results? We know that all the values sum is always going to be greater than 5, which means it is going to be shortening the reach we will have to search for. That is a good benefit. Second benefit is that it will allow us to handle the duplicates in a more elegant manner. So what I'm suggesting is that let's say that in this case, we have the values 1, 2, 2, 3 and 4. This is the input we are given. Now what we are doing is that logically it's very simple. We are just simply making decisions. And what is the decision we are making? We are iterating over the very first element. Okay, so let's say that we are currently passing through value number 1. We know that the target has to be 5, but our current sum that we have made so far is just value number 1. So we will need to add some more subsequent values. So let's say we decide to add value number 2 down this current path. So now the sum is 3, still less than 5. So once again we decide to add value number 2. So after adding this value, our sum becomes 5. So the moment our sum becomes 5, whatever the values we were currently having as part of our path, this is one of the potential answers. So let's mark this as part of the answer. Okay, that we currently have found one of the combination 1 to 2 as part of the answer. After doing this, there is still more possibility that we could have some other value that we might have missed on. So we will have to backtrack and once again see for other possible answers. So let's say that we do a backtrack at this position number 2, and once again this now the problem comes, because this next element is already 2 and we just did a backtrack. But the thing is, we already considered this 2, so now we will have to consider value number 3. Okay, so let's say if we try to do this one, this current sum becomes 6. So the moment current sum becomes 6, we know that this is no longer a viable solution, which means we will have to do a backtrack because this solution is leading to a value greater than 5, and once again we will have to repeat the operation for all the other remaining possibilities. So we remove value number 2. So once again, now with this value number 1, there might be some other solution with 1 and 3 that we could make. So we try to add value number 3. After this value number 3, the current value is 4. After 4, we add value number 4 over here. So doing this also brings our sum greater than 5, which means we will have to do a backtrack. We do a backtrack and we get rid of this value number 3. Now at this value number 1, we still have possibility to check for value number 4. There is still one more decision we haven't made. So let's say we do this one. The sum of this is actually 5, which means we found another set that corresponds to our correct result and our correct instinct. So we are going to mark this as part of the answer as well. Now once again, we know that we took care of all the things we could using this value number 1. So now we are simply going to go to the next element and not even consider 1, because we ran through all the possibilities we could with value number 1. So we don't have to worry about it. Now at this value number 2, let's say, let me just clean this up a bit. Now we are making a new decision tree, a new decision path where we have 2. Once again, we go to the next element, that is once again 2. After doing this, we go to the next element, that is 3. So now this sum in total becomes 7. So 7 is greater than 5. If 7 is greater than 5, going down this path 2 does not make sense. So we are going to ignore that. Ignoring this, we are going to be going with 3. So we are at this juncture and we found that current sum is 5, which means this is one more potential answer that we will have to record. So let's mark this one. Okay, marking this, we are not done yet because we may still find another results, we don't know. So we go to this next element 2 to 4, but this also leads to result number 6, which means we calculated all the possibility at this current 2 as being the very first element where we are calculating. Now the thing is, next element is also value number 2, and we can see that with previous element 2 we already calculated all the possibilities. So if we had a target value, let's say instead of over here instead of 5, if we had a target value 4, we would have a potential value 2 that is being generated by this 2 already. So we don't have to do anything over here. And also if we try to go down this path, let's say that we ignore my advice for now, and we say that currently we took care of this one, we took care of this 2, this 2 is still valid and legitimate. So now we have this value number 2. Once again we go down to the path, so we find value number 3 as the next potential match, and this matches. So should I add it to the answer? No. Why should I add it? Because I already calculated this one. So what I'm suggesting is that once we have the sorted list, we simply check that for any particular element that we are trying to iterate over in the recursive manner using our backtrack function and recursive function, we first check that whether if it is the same element as the previous element. If that is the case, we already calculated all the possibilities and added to our answer, so we can simply ignore that. So now we are all going to be ignoring this 3 as well. Now we are left with this element number 3. So let's try to make possibilities with this 3, and we are just going in one direction. We are not going in the opposite direction because we calculated all the possibilities. So with this 3, the only possibility we have is to add value number 4. The sum is going to be 7, so greater than 4, which means this leads to no result. So we already calculated all the possibility as 3 as well. Next is the only element 4. Once again, if we calculate the possibility, there is only going to be just element number 4, which is not 5, so we cannot put it in the answer. After this, we are done with all the elements in our input, and this is the answer we need to return. So now let's do a quick recap. What we did, we calculated that what was the backtracking function, and we also calculated that what is going to be a recursive approach. For a recursive approach, we need two items. We need a base case and we need a recursive call or recursive function. We know that what is going to be our backtracking logic, that at every possibility, the moment we either reach to the target value is equal to 5 or target being greater than 5, in either case we are, if it is 5, we are going to be adding it to the answer. If it is greater than 5, then we are going to be going to the very previous element that we were iterating over and remove that from our current list and follow along with the remaining possibilities. That is option number 1. For our recursive, the logic is quite straightforward. Base case is going to be that the total sum of the current elements that we are iterating over, it's either 5 or greater than 5. If it is equal to 5, we add it to the answer. If it is greater than 5, then we can simply just move forward or jump to the next element. And for the recursive function, we are simply going to go in a normal fashion by adding the current value and removing the current value from the given input array, and just making a recursive call by adding a new value that is next inside our given array. So if we see the coding solution, it would make much more sense, and this is, in my opinion, a very beautiful solution. So I hope you understood what I was trying to explain. Now let's quickly see the coding solution for this one. So here is the coding solution. First of all, we are generating our result where we are going to be storing the list of array list. Then we are sorting the given candidates array. Plus we are going to have our backtrack recursive method where we are going to be doing backtracking and also making recursive calls. And so now let's understand our backtrack method. So first we are passing in the result list that we just created. We are also maintaining a current list. We are also maintaining the candidates array that we are iterating over. On top of it, we have provided our target and we have provided our start values. Okay. Very first thing we are doing is checking that if the given target is equal to 0, then we are going to be adding the current list inside our result, and we are simply going to do a return from our current recursive call. If that is not the case, we will run our for loop where we are simply going to iterate over all the values that are currently present inside the candidate. Very first thing we are doing is skipping the duplicates. So we are checking that if the current candidate is same as the previous candidate, we can simply ignore that value. Next, we are also doing an early termination if the sum becomes negative, because at every given moment, the moment we see a new ith value, we subtract that ith value from the given current target element, and the moment we realize that this is going into the negative, we are simply doing a break operation. Now if that is not the case, we add the current value to our current array list that we are maintaining. Then we once again make a recursive call with the current value, which contains one more value right now, and we provide the target minus candidates I, because we are subtracting the value from the target that we need to achieve, and we update it with the next element inside our for loop, and that's it. Now once we get a result back from our backtrack, we simply remove the very last element, and we once again do the same operation for other possibilities that we are yet to calculate. So this approach should work. Now let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs pretty fast compared to a lot of other solutions, which is pretty good. So once again, I would be posting this solution in our GitHub repository, so you can go and check it out from there. Thank you. Hello friends, we are still not employed by a FANG company, so let's not stop lead coding till we get there. Today we are going to do word search lead code problem, and if we see the number of companies where I want to work at who have already asked this question, there are companies like Amazon, Twitter, Microsoft, Uber, Bloomberg, Facebook, TikTok, Snapchat, Google, Apple, Samsung, Roblox, Goldman Sachs, ByteDance, and eBay. So these are really popular companies, and this problem is really popular because it has very real life applications. We have all played games like crosswords and Wordle on our phones and on the newspapers and different kinds of stuff. So that is where this problem is associated with, and we are going to see that how to solve this one. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a lead code medium problem, and basically we are given an m cross n grid of characters called board, and we are also given a string called word. Now we need to see that if this word can be created based on whatever the number of characters we are given on this board, and if it does, we need to return true, else we need to return false. Also, we are given a note that the word can be constructed from letters sequentially adjacent cells, where adjacent cells are either horizontally or vertically neighboring. And we are also told that same letter cell may not be used more than once in order to create that word. So let's try to understand this with an example. Over here we are given this big board, and on this big board we are told that we need to find the word A, B, C, C, E, D. So if we see over here on these marked values, so this starts with the word A, the neighboring word is B, the neighboring word is C. Again, we are told that we can horizontally or vertically see the words. So if we go vertically downwards, we see another C, and then we find another E, and at the end we find D, which is also adjacent to E, which is this letter, and this is basically part of this given board. So in this case we can return true. Now suppose if this word if we were not able to construct this word, we would not return true and we would return false. So let's see that what would be the optimal approach to solve this problem. Well, we have actually solved similar problems like this in the past using DFS and backtracking, and this is what we are going to do for this problem as well. Let me quickly show you how. Okay, so suppose this is the custom example we are given, and we need to find the word spider to see that whether it exists on this given board or not. And the idea is actually quite simple. What we are going to do is, first of all, we are going to take the first character inside this word, which is S, and we are going to iterate over this matrix until we find this first character. The moment we find the first character from whatever the place is, then we will keep on trying to find the next letter, the next words inside this word, to see if it exists in the neighboring node or the neighboring cell of the board inside this given matrix. And if somehow we are able to reach to the end of this word, we can return true. If we don't reach the end of the word and we actually reach the end of the matrix, we can return false. So the idea is actually quite simple, and there are just few tweaks we will have to use in between. So first we will start iterating over this matrix, trying to find this word number S. Now this is not S, this is not S. Over here we find the first value as S. So because this is the first value as S, now we will have to try to see that whether this P exists or not in the neighboring node of this S. We can clearly see that P exists. But before doing that, what we are going to do is we are actually going to mark this node as visited. So one way to do is to use some visited hash set and store all the values, but that is just causing strain on and to have an extra memory usage. Rather than doing that, we are going to actually modify this input, and we are going to mark it something like hash or something, which is an invalid value and it can never be there. So which means at any point we encounter that this value is hash, we don't need to go back to that place. Now we will start iterating over the neighbors of this S. So neighbors of S can be these three places. If we try to look at these three places and we are looking for the alphabet P, so P is present over here, which means that so far we have found S and P. Now we will update our value to I, and we will try to look for I in this P's neighbor. Also we will mark this node P as like hash, so we don't come back to this place again. Now this P has only two neighbors because this neighbor S has already been visited because its value is hash, so we can't do anything about it. Now we are looking for this letter I, and we find the letter I over here, which means again we will mark this as hash. We will update the value of word we are looking for. The word we are looking for now is D. We will try to find the neighbors of I and in the neighbors of I, okay, we don't find anything over here. This is not D, and this has already been visited, which is hash, which means that there is no neighbor of I that contains this value D, which means that now we haven't found the word so far, and we still have matrix to go to that we haven't visited so far, which means that now we will backtrack from this I to the position we were originally at, which means that from this I we came from P, from this to this P we actually came from S, and now we can say that okay, even in this S it does not lead to us to find this word, and then we will again proceed with our search. So again we are trying to find this letter S again and not the D, because we did not find anything in the route, which means that now okay, this P is not S, this I is not S, this T is not S, so we are good so far. Now at this position we find a letter S, which means that okay, this S has been found. Now in the neighbor of this particular cell we will have to find the letter P, and we are going to mark this S as hash as a way to identify that this has been visited. Now what are the neighbors of S? These four are neighbors of S, and the one value we can find where the P exists is this one. So again we will repeat the same process. We will mark this as a hash. We'll try to find the word I we will find over here. So again we will mark this as a hash, and we will try to find D in the neighbor of this I. So we find D over here. So again we will mark this as hash. We will go update the word we are looking for, and now we will try to search for E inside this D's neighbors, and we can find it over here. Again mark this and then try to find this R. So R we actually find in the neighbor of this one, and this is the correct R, which means that now we are able to reach to the end of this word list, and we can return true in this case, saying that okay, this actually exists inside this given board, and we will be good. So this solution works perfectly fine. Let's see the time and space complexity with this one. So for the time complexity, actually the time complexity is a little bit tricky to find. Why? Because the time complexity is actually big O of n, which is the number of cells. So for every single cell we will have to iterate at least once. So n is given, but then we will have to repeat the same process for 3 times to the length of L in the worst case scenario. Why 3 times to the length of L? Because notice that at any single position, suppose we were at this position number D, and we need to see that okay, whether the next value E exists or not. So we need to check 3 places, not this one, because this already has the value hash, which means we won't check this one. But we in theory we might have to check at all 3 places, and imagine if all 3 of them had the value E, we might have to explore the paths on all 3 of them in order to find the next value R. So that is why at every single position N we actually have 3 different options to see that whether this word exists or not, and this L is actually length of the given word. So that is why this is the time complexity. In terms of space complexity, we actually need to store the value inside our space until the time we reach to this entire word. So it would be big O of L, where L is the length of the word that is given. And this time and space complexity works perfectly fine, and I hope this solution makes sense to you. Let me quickly show you that what would be the coding for this one. So for this word search problem, we will actually have to create a backtrack public method that will call itself, and recursively we will try to achieve its answer. So there are some variables that we will need in both in this boolean exist method and also in the new backtrack method that we are trying to create. So let me define some variables that are global and that we can use in both the methods. And the variables we are going to create is to store the value of this board, and we will also need the row and column size of this given board character array. Now we have these, we will assign values to all these 3 variables from these given input endpoints. Once we have this, we will have to iterate over this board character array. So we are going to assign 2 for loops, and for both the for loops we are going to have the I and j value iterate up until the point of this rows and columns, and inside this for loop we will call our backtrack method. Now inside this for loop, we are going to call our backtrack method, and we are going to have backtrack method return a boolean reply, either true or false. And inside the backtrack method, we are actually going to pass in the values of the current row position, current column position, word we are trying to find, and the index value we are currently at. So for the index value, we would initially start with the position 0, and we would increment it every single time inside our backtrack method. And if at any case this returns true, we can simply return true in this case. And somehow if we are able to complete this loop and get out of it without returning true, which means word does not exist, so we can return false. Once this is done, now we will create our public boolean method called backtrack. Now first of all, we will check that what is the condition where we will need to return true. So if at any point we identify that the index value is actually greater than or equal to word length, which means that we have already found that the current word already exists inside our given character array, so we can return true in this case. So now we will try to find the terminating conditions, and inside the terminating conditions, first of all we will check that whether the row and column position, are they going out of bounds or not. If they are going out of bounds, we can return false immediately. If that is not the case, we will try to see that the current value we are looking at inside our board, if that value is not in sync with whatever the index value of the word we are looking for. If that is not the case, we can also return false immediately. So if any of these conditions are true, we can return false immediately. None of these conditions are true, which means that the current index value actually matches the value of that row and column position inside the board, and now we will have to iterate over the neighbors of this current row and column value inside the board. So in order to iterate over the values of the row and column, we are actually going to have two arrays called row direction and column direction, and that will help us navigate all the neighbors of any particular cell. Also, before moving to the next element, we are going to mark the current row and column position to have a value called hash, so we avoid checking the same element twice. Okay, once this is done, we will also have a boolean variable called return, and initially we are going to initialize its value to false, because basically we are going to call the backtrack function for all the four neighbors of the current cell. So for that we will keep track of this ret variable, and we are going to run a loop to iterate over all the directions, and we will add the values of these row direction and column direction to subsequent row and column positions inside this recursive call to our backtrack function. We will also update the value of the index, because we can determine that we have already find the word inside the previous index, and that's why we are calling the next index value to be searched inside the neighbors of any given row and column position. And also at any point, if we identify that the answer of this return function is actually, or this return variable is actually true, we can break out of that particular element immediately, and we don't have to check all the other neighbors. So we will put that condition as well. Once that is done, basically we are done with the checking part. Now the only thing we need to do is we will have to update the value of the row and column position to whatever the value that was originally there, and in the end we can simply return whatever the answer we got for this ret function. This is pretty much it for both our backtrack method and also our main method, and this should be able to solve our problem. Let's try to run this code. Okay, seems like our solution is working. Let's try to submit this code, and our solution works as expected. And I would be posting this in the comments, so you can check it out, the solution from there. Hello friends, we are still not employed by a FANG company, so let's not stop lead coding till we get there. Today we are going to do word search to lead code problem, and if we see some of the companies where I want to get a job who have already asked this question, there are companies like Amazon, Uber, Microsoft, Google, Snapchat, Facebook, Apple, Twitter, TikTok, Bloomberg, Spotify, Twitch, and Airbnb. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is the lead code hard problem, and basically we are given an m cross n matrix of characters. Now, and we are also given a different list of string called words. Now we need to return all the words that are present on the given board. We are also given one more thing, that each word must be constructed from the letters that are adjacent to each other. So, and we are also given the definition that what adjacent cells are. Basically, any cells that are horizontally or vertically neighboring to each other, we can consider them to be a part of the consecutive sequence series, and we can use them to create words. So let's try to understand this with an example over here. Over here we are given a 4 cross 4 matrix, and for this matrix we are told that these are the list of words. We need to check that whether they are present inside this given matrix or not. So if we try to just look at this example, basically we can see that this first word oath is actually present over here, where O, A, T and H, they are creating or forming this word, and if you see, they are all sequentially adjacent cells to each other. So that's why we can use them to form this words and see whether it's present or not. So in the answer, first of all, we are going to add the word oath as one of the answer. Then if we look at the answer, we can also find this word eat to be present. So E, A, T, that is present in this manner. And again, though this is on the left side, this is not the conventional way to write it, but still based on the adjacent cells, we can actually form this word eat, and that's why this eat is also going to be part of the answer. So we will add eat in the answer as well. Now for this two, PEA, P and rain, these two are not present inside this given matrix, so we will not include them in the answer, and this is the answer we will have to return. So basically it is one kind of a word search game or word search puzzle. So that is why the name is word search 2, and this is the little bit of advanced version. So first we'll see that what is going to be like a basic, very trivial approach, and then we will try to improvise using a different set of data structures. Okay, so most basic idea we are going to have is that we will start iterating over all of the characters that are present inside this m cross n matrix, and then for every single character we are going to see that whether that matches with any of the starting words or not. If we find a potential match, then we will try to find the subsequent character and the neighbors of that particular character to see if we are able to generate any exact word or not. And the moment we do that, we will actually put it in a new variable called answer, and that is how we will be able to generate our answer. So let's try to see this in action. So first character in this case is X. So X matches with this character over here in the given set of words. So next we will have to see that whether any neighbor of X is actually Y or not. Neighbor of X is actually H and A. We do not find Y over here. So because we do not find Y over here, this X does not lead to anywhere. So we can mark this as visited. That does not lead to any answer. Next character is H. So H matches with this first character, and then we will have to see that whether B exists as one of the neighbors of H, and B also exists as one of the neighbors of H, and then the subsequent character O also exists as one of the neighbors of B. So in this case, this HBO is actually a complete word we are able to make based on subsequent characters that are present adjacent to each other inside this given matrix. And because of that, we are going to create a new variable called the answer, and in the answer we are going to add the value HBO over here. Now we will start iterating over this A. So again, A is the starting point over here, and next character B and C, we are able to generate this pair using sequentially iterating over. And if we see over here, we can also generate this A, B, C in this fashion. Now this character is Y. So again, Y is not part of starting character of any other word, so we cannot do anything about this. Our next character is again C, that we have already visited, so we don't need to visit this. And next character is Z. Z again is not the starting point of any of these characters. So in this case, this is the answer we are going to have, and we can return this one. This solution works as expected. There are no issues with this one. But if you just see, we only have a 3 by 3 matrix, and for every single character, in the worst case scenario, we might have to iterate over every single word and check that whether it matches the starting word or not. We can maybe simplify using a hash map, but the thing is, this is still going to lead to a very bad solution. In terms of time complexity, this is going to be disaster, because for every single character, we might have to iterate over every single word that there is, and once we find a match, then we will have to iterate over all the neighbors of that particular character as well. So that leads to nowhere. So let's try to see that where we can find a better time complexity, and the solution to achieve a better time complexity is actually using a new data structure called try. Now I have already extensively worked on try, and you can find all of those solutions over here. Check out this video if you want to learn that what a try is and what are its applications. Now let's see that how we are going to use try in this case to improve our performance. Okay, so the previous example we see, basically what we were doing is we were iterating over every single character, and then we were trying to see that whether that character matches the first element or not, and sequentially we will have to check every single word that was present. And if we find a potential match, then we will have to check all the neighbors to see if the next consecutive element is present or not. And that was the major reason that why we were having a disastrous time complexity. So in order to improve that, if we can find some way to eliminate this checking procedure, that for every single character we might have to look up all the elements or all the words that are present, because imagine if there are million words present, we might have to check million times, and then that is going to be very disastrous. The idea we are going to use is that whatever the words that we are given, we are actually going to convert these into a try. And because we are converting them into a try, for any character, searching that whether it is the starting point of any word or not becomes pretty easy for us, and we can actually do it in nearly constant time. Because in the try it is very fast and efficient to find that whether any word exists or not, and if it exists, it is very easy for us to iterate over that particular word or not. So first of all, let me quickly create a try block based on these three words. The try block is going to look like this. So based on the words that we were previously given, we actually created a try block. And now using this try block, we are going to make things pretty easy for ourselves. Basically, we are going to iterate over in the same fashion for the given matrix. But this time all we will have to see is to look up in this try that whether the current character, if that is any children of this given root node or not. And if that is the case, we will keep on iterating. So first we find this character to be E. E is not part of any children, so we can ignore that. Next one is F. F is actually part of a children. So okay, now we have found F to be part of the children. Now we will have to see that what is the next character in this try block. So this next character is A. So we will have to see that whether any neighbors of this F is actually A or not. So we will have to check on three sides, and we find a match over here that this is A. Okay, now again next character is A. Again this neighbor is actually A. Okay, now this character is N. So again neighbor of this A is N present over here. And again the next character is G. So G is also present over here. And since we have reached to the end node inside our try, because of that we can conclude that the whole word was actually present inside this given matrix, and we can return true in this case, and we will add it to our answer list. So inside the answer list, the first word we are going to add is fang, that is present inside this given matrix. So see how easy it is for us to find these things. And okay, now the next character is R. R is not children of any of these root nodes. Next one is T. T is also not a children. L is not a children. These are all visited. Now this G. G is actually a children. So now it becomes easy. Now we will have to start iterating over. Okay, so we are at this position G. Now the next element is O. The next element is O, and O is also a neighbor over here. Okay, so which is good. Now the next element is O. Again, O is a neighbor over here. So which is good. Now this next element is G. G is also a neighbor of this O, right? So we are good up until this point. Now we have to find this L. Now, if we look at this G, we do not find L to be a neighbor of this G. So because of that, we will actually have to roll back, and we cannot move forward with this path. So now we would have visited this G, and that did not lead us to anywhere. So again, we will start with our routine procedure. Okay, now this next character is O. O is not starting point of anything. T is also not starting point of anything. G is we have already used it. Now this is again G. So again G is the starting point of this one. Next character is O. O is present over here. Next character is O. O is also neighbor of this one. Next character is G. G is neighbor of this one. Next character is L. L is neighbor of this one. And next character is E. E is the first character. And because we reached to the end character over here, we can conclude that Google is also present inside this given matrix, and we will add it to our answer. So we will add one other entry called Google. Okay, and now next again this character is L. So L does not lead to any children of this root node, and F does not lead to any children of this root node. So in the answer we are going to return this Fang and Google to be the answer, and this would be the most optimal way to solve this problem. Remember, because we used a try block, things becomes much more faster for us, and we can immediately look up that whether any single character that leads to an answer or not. Okay, now let's do the tricky part. We will have to do the time and space complexity analysis. So for the time complexity analysis, it's actually a little bit tricky. The first thing that is a given fact is that we will have to iterate over every single character that is present inside this given m cross n matrix. So that's a given fact. Suppose that the total number of cells that are present are actually m. So now, okay, we already know that that is whatever the time complexity is going to be the factor of m. Now for this particular m, imagine that for any particular character, what is the maximum work we will have to do in the worst case scenario? Well, the maximum work we will have to do in the worst case scenario is that any particular character, suppose this f matches this character that is present. Now, whenever we find a potential match, we will have to look for the next element in all three directions of that particular word. So suppose this O was a potential match, we will have to iterate over all four directions in any given case. So for any single cell, we might have to iterate over in the all four directions, and for all four directions, the number of traversal that we will have to do for each one of them would depend on the next three or the next remaining three characters. Because remember, for this Google, suppose we find a match, this O to be a match. Now the moment we find this O to be a match, again we find this O to be a match. So now because we find this to be a match, we do not have to look for this particular element, we will have to look at the remaining three positions. So then we will have to, for any single character, we will have to look in the four directions, and for all the subsequent elements, we will have to look in the remaining three directions, and that we will have to do depending on the length of that particular word. So for the remaining three elements, we will have to iterate over to the length of that. So that's why 3 to the power of L minus 1. And why minus 1? Because for this first character, we are actually looking in the worst case scenario in all four directions, and for all the subsequent length parameters. So suppose for this particular Fang, for this F, we might have to look in four directions, and for this A, we only have to look in the remaining three directions because one adjacent cell is already F, so that we do not have to look at. So this is going to be the time complexity. So if I write the final time complexity, it's actually going to be big O of m into 4 times 3 to the power of L minus 1, and that is the final time complexity. This is a very difficult time complexity analysis. So yeah, it gives you an idea that why this problem is pretty popular. If we see space complexity, that is pretty simple. Space complexity depends on the total number of words that are present. So suppose we sum that up to big O of n, where m is the total number of characters that are present in the initial word list. So after doing this time and space complexity analysis, now let's move on to the coding. Before we implement our solution, we are actually going to create our class try node. In the class solution, we are going to define a couple of global variables. Now inside the find words method, first of all, we are going to initialize our try block, and we are going to add all the words to our try block. After creating the try node, now we are going to start working on backtracking, starting with each cell in the board. So first of all, let's create the board variable. And now we are going to initialize couple of loops to iterate over this full board matrix. So now for every single position inside this given matrix, we are going to check that whether that is actually any of the children of this root try node that we have created. And if that is the case, then we will create a helper method called backtracking, where we are going to iterate over all the adjacent cells of that particular row and column position, and also that particular entire DFS traversal for that particular branch inside our try node. After this loop ends, basically we should have populated our answer inside this answer variable that we have created, so we can simply return that. And now let's create our backtracking method. So this is going to be our recursive method. First of all, we are going to define a couple of variables. First of all, we are going to check that whether the current node is actually a word or not. If that is a word, we can immediately add it to our result. Okay, if that is not the case, we will have to start doing our traversal. So how we are going to do our traversal? Remember, whatever the current row and column is, we cannot use the same word again. So we are actually going to mark this as hash in a way for us to identify that that is the node we have already visited. Now for any given row and column, we will have to iterate over all of its neighbors. So we are going to use couple of variables to our advantage. Now with the help of row and column offset, it becomes pretty easy for us to iterate over all the neighbors of any given node. So now we are going to run a for loop and we are going to iterate over all the neighbors of given row and column position. First we check that whether our new row and new column, if they are going out of bounds or not. That is the case, we just simply ignore that. Otherwise, if we are at the correct neighbor, we need to check that whether that neighbor is actually subsequent character that we have already stored in our try or not. And if that is the case, we are going to call our backtracking method again. Now after our exploration ends, basically we will have to put back this hash to its original position, and that should be it. There is one more optimization we can do, and that is to incrementally remove the leaf nodes, which means that whenever we identify that the current node's children, if that is empty, then basically we can just remove that from our parent. That should be it. Let's try to run this code. We will also have to update the value of the node in the else condition. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs pretty efficiently. I would be posting this in the comments so you can check it out from there. Thank you. So the lead code problem we are going to solve now is called palindrome partitioning. We can see that this one is a medium problem, but in my opinion, this should have been a hard problem. We can see that this is a very well-like problem. Now let's understand that what is being asked us to do. We are given a string s, and we need to partition this string s such that every single substring of that particular partition becomes a palindrome, and we need to return all possible palindrome partitionings of s. So it sounds a little bit awkward, but let's try to understand this with an example. First, let's understand that suppose we are given a string s such that the values are a, b, c. So we can see that in this case, if we have to partition string, there are a bunch of different options. We can have a partition that is completely like this, or we can do a partition like a, b, and c, or we can do a partition like a and b, c, something like this one, right? There are a bunch of different ways for us to partition any given string. But the thing is, in this case, we need to find partitions such that every single partition becomes a palindrome. Now we all know that what is the definition of a palindrome. Suppose we are given a value like this ABA. In this case, this ABA is a complete palindrome. Why? Because if we write it from left to right or right to left, in both the cases, the answer is just going to be ABA. So same way, this let's say if this is the input we are given, and if we have to partition it in such a manner that every single substring of that partition becomes a palindrome, we only have one possibility. That possibility is if we partition it by using just individual characters, because an individual character in itself is a palindrome. Because let's say if we only have one value, you can read it from left to right or right to left. In both the cases, we are going to be left with the same value. So this is the only answer we need to return in this case. But let's say that we may have been given some other options. Let's say that our given string s is equal to values such as a, then a and b. Okay. Let's say our given string s is equal to values a and b. So now in this case, we will have two options in order to generate the partition. First partition is going to be quite straightforward, that is taking on individual characters because they are palindrome and their own, and combination of these characters actually form in such a manner that every single character is a palindrome in itself. But we can make one more distinction or one more answer in this case, where if we create a partition of these two values a as one partition, and we create another partition of this individual character b, then also this becomes a valid partition of the substring such that every single portion of the partition actually forms a palindrome, because this a is a palindrome and this b is a palindrome in itself. So this is what the problem statement is actually asking us to solve. Now let's try to understand some logic on how we can actually solve this problem. Well, if we just have to solve it using pen and paper, what is going to be the first logic you are going to apply? Well, the very first logic is that we will start iterating over this given string character by character, comparing every single character with the previous characters that we have been able to find so far, to determine that whether using the combination of previous characters are we able to generate palindrome or not. If we are able to generate a palindrome, we would mark it as one of the partition, and then we will keep on moving forward. So let's try to understand the approach I'm suggesting. Let's say over here we start iterating over at this very first element A. Now for this very first element A, the moment we come to this element A, we have two choices. One choice is that A in itself could be a palindrome. So we mark A as a palindrome, and same way there could be another possibility that we may find some value where this A could be potentially part of some future palindrome that we are yet to discover. So let's leave this possibility open for us for the moment. Okay. Now, if we decide to create a partition based on A, then once again, we have the option to move forward with a single A or the next element. So let's say that once again, we decide to move in with a single A and create another partition, which this is the first partition and this is the second partition. Okay. And once again, we move to the another value. And for this next value, we encounter value B. So once again, we create a partition in its own. Now the thing is, when we reach to this B, we realize that now we have reached to the end of our array. So far, all the values we find inside or all the partitions we did for our given string S, all of these values are palindromes, because let's say that in order to determine that whether any particular string is a palindrome or not, we are actually going to create a method that checks that if the given string is a valid palindrome or not. Okay, and this string is quite straightforward. They are the values of itself, so we know that all of these values are correct palindromes. And we are also storing some current array list where we are keeping track of all the current values that we are iterating over one by one. So we realize that this is the correct sequence of the partition that generates a palindrome. So we are going to mark this option inside as part of our answer. After marking this, we are not done yet, because once again, I mentioned that there could be some potential ways or some potential other paths that we are able to generate, which could lead us to more palindromes that we are yet to discover. So once again, let's try to apply that same logic in this case. So now, once again, we already explored this path. Okay. Now what we are going to do is we will do a backtrack operation once again to the very first character to make sure that maybe we did not miss out some palindromes that we could have found. So let's say that we, instead of just creating a single value partition, from this single value, we actually decide to do a partition of two values. So creating a partition of two values would give us value AA. Once again, we check that if is this a valid palindrome or not, and yes, this is a valid palindrome. So we are good to continue to the next element. For some reason, if we identified that this was not a correct palindrome, let's say for some reason that this value given is X, so then this AX is not a correct palindrome. If this is not a correct palindrome, then it does not make sense for us to continue down this path of partitioning. So then we would choose a different path where after this AX, we would actually include B in our decision making as well. But there is no need to do that. So let's leave it as it is right now. So after leaving it as it is, okay, so we created another partition at this moment AA. The answer is valid, legitimate. So we are keeping it as it is. After keeping this as it is, now we decide to go to make another partition, that is this value B. So once again, we create a single partition of just one value B. This is also a palindrome. And with this B, we reach to the end of our list. So after reaching to the end of our list, we are also going to be marking this sequence that we found as part of the answer as well. Now let's try to clean this up a bit. And now once again, we are yet to explore more possibilities that we haven't found. So we will also try to do this one. Now for the more, initially we took down a possibility where we are only partitioning the string based on just one value. Then we partitioned the string by using values a, and then also it worked out. Now we are going to partition the string based on considering all three values. So let's say that we just create a partition that is a, and b. Because this is definitely not a palindrome, plus we reach to the end of our list. So now we are done with our search with starting all the possibilities from this current value a. Now we are yet to identify more possible palindromes that we are yet to identify. So let's say that in the very first beginning when we made this partition, now we will continue down this path, but previously we went down this path, that was this answer over here. Now we will try to choose a different path, and in this different path what we are going to do is, with this a, now we are going to pass the baton on to the next element, and now we will say that, hey, next element, if you want to do or try some partitions, let's check those. So once again from this a we can create another partition like ab, but definitely this partition is not a palindrome. So if this is not a palindrome, then it does not make sense for us to continue down this path, and anyways we are running out of elements in this case. But let's say if we had some more elements over here, let's say some more element like say c. So do you think it would make sense for us to create a partition such that a, b, and next element to c check like this? No, because we already know that this is not a palindromic substring. So why even bother checking? So then in that case, our logical step would be to include c as part of one of the possibilities as well. But once again, this is also not palindrome. So now we can be done with this. So this is the simplest approach we can take to solve this problem. Now we all know that what we did. We use the backtracking option to basically go through all the possibilities that we can in order to generate or find sufficient answer. Now let's try to understand that what has to be the logic of our backtracking function. This is going to be a simple function that takes the current partition that we are dealing with, and based on the partition from the input string, it is going to have a starting index for the next partition that we are going to check with. And with the starting index of the next value, we should be able to understand that are we at the end of our string or not, and whether we can conclude the current partition to be over or not. On top of it, with every single value, we are going to check for any particular substring that we are generating, that whether that is a palindrome or not. And in order to do that, in order to accomplish all of this, we will actually use recursion. Now for recursion, we know that we have two items that we need. First one is a base case and second one is a recursive function. Base case is quite straightforward, that if I previously mentioned that we are going to have a variable called start to keep track of the next index. That would be the starting point of the next sequence of palindromes. Let's say that we created a subsequence like this, AA as one of the palindrome, then start index would be living over here with value number 2, as that is the logical starting position. So we are going to check that if for the current list we come to a place where the starting index is the length of the given string, then we are going to be marking that current index as part of the answer and returning or coming back through our recursion. So we identified our base case. For the recursive function, we will have to do two things. First thing is that for every single new partition we make, we will have to check that whether this one is a valid palindrome or not. If let's say that is a valid palindrome, then it would make sense for us to call the recursive function once again with the next value in line and creating the current partition as it is. Now I know it sounds confusing, but if you just understand that or try to walk over the solution that I presented, then it would make absolutely beautiful sense to you that what I'm suggesting. And on top of it, for the recursive function, we are also going to be updating the current index value that we are iterating over. Let's say that we iterated over AA. So then we will have a recursive function starting with value number B. And once again, we will try to repeat the same process. Combination of all of this should give us the answer. But thing is, this is not just enough. Once we receive a call back, and we will have to check for other possibilities, where first we check for the possibility of A only, then we may have to check for the possibility of AA. So in order to do that, we will have to do a backtrack. And for the backtrack, the simplest thing is to remove the very last element we added inside our current array or current array list, and once again repeat the same operation. So basically combination of backtracking and recursion is the way to move forward in this case. Now let's try to calculate the time and space complexity. Well, time complexity is difficult and tricky to calculate in this case because we don't know that how many number of potential partitions we can make. So at the end of the day, this is simply a decision making algorithm, and in the decision making algorithm, at every given step, let's say that we created a partition like this A. Now we will have to check whether to include this A or not to include this A as part of the partition. So at every given step, we are checking for to whether to make that decision or not to make that decision. So basically we have 2 to the power of n possibilities, where n is the number of characters given, and for every single character we will have to repeat the same operation. So it's going to be n multiplied by 2 to the power of n possibility, and that's why this is a very expensive operation. And if you go through the lead code problem, we are only given like up to from 1 to 16 as part of the range of n for the length of the string, because they also realize that they don't want to put much load on the lead code servers. So now let's try to quickly see the coding solution for this one. Okay, so the very first thing we are doing is that we are generating a new result array list that is going to store different array list inside it to store our answers. Then we are going to have our backtrack method where we are passing in first of all the result array list we created. Then we are also passing in the current list we are iterating over, passing in the given string that we are given as the input, and we are passing in the starting value of the next pointer that we should consider for the partitioning. This is the starting pointer that I just mentioned. Okay, now first of all, let's see in our recursive function we are going to have our base case where we are first checking that if the starting value is the length of the given string, which means we are actually reached to the end of the string, so we can add the current result we are iterating over inside our result array list, and we can simply do a return call from the iterative stack. And now let's check our recursive case or recursive function. So for that we are basically iterating over from the starting index till the end of this list, and we are updating the value. And here I mentioned starting and ending pointer. This is just simply so that we can check that the given palindrome or the given sequence of element partition we are iterating over, if that is a substring or not, we can simply make that call. So first thing we are going to check is that if the given current substring, is it a palindrome or not. For that we have created is palindrome method where we are doing nothing but we are simply iterating over from both ends, like starting pointer and ending pointer. If at any given moment we identify that there is a mismatch, we simply return false. If that is not the case and we complete the whole iteration, then we can simply return true, saying that this current substring is a palindrome. Okay, after determining that the current set of partition is a palindrome, we are going to add that substring to our current list that we are maintaining, and once again we are going to recursively make call with the same values except the next index position that we will have to iterate over, and that is going to be our end plus 1. You can also define this end instead of end to be I as well. I just put in end for it so that it becomes better readable for our is palindrome method. And once we get a result back from our backtrack method, we are simply eliminating the last value we inserted inside our current list, because we still have to explore more possibilities. And this is our backtrack function basically. So now let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs pretty fast compared to 98% of all the other solutions, which is exceptionally good. Once again, the solution of this code is presented on our GitHub repository, so you can go and check it out from there. Thank you. Okay, so now we will attempt to do a very scary question that is called N Queens. Now, in my opinion, this is one of the most toughest and most interesting problem I have seen. Basically, this one is a lead code hard problem, and very justifiably. It is also an extremely well-liked problem, and let's understand the statement. The n queen puzzle is a problem of placing n queens on an n cross n chessboard. So if we are given, let's say, 4 by 4 chessboard, we will have to place 4 different queens. Now we know that every single queen can iterate in 3 directions. Let's say that if I decide to place a queen over here, then this queen can control these squares, and these squares, because queens iterate in all 3 directions. So based on considering a formation such that I am able to place 4 different queens, and without these queens intersecting with each other on a given n cross n board, and I will have to make sure that I populate all the n queens. Now let's see that what else is being asked for this problem statement. That we are being told that we are given an integer n that defines that what is going to be the size of the board we are dealing with. Now we need to return all the distinct solutions to the n queens puzzles, and good thing for us that we can return the answer in any order. Now there is also one more just a quick note, that each solution contains a distinct board configuration on a place where the queens can be placed. Let's say that if I decide to place a queen over here, then next queen might be placed somewhere over here, because I need to avoid hits by this queen. So there can be one solution or 2 solutions or 3 solutions, no matter how many solutions are there, where I can place all 4 queens on this 4 cross 4 board. I will have to put all of those solutions inside the answer. Next thing is, we are being told that where we are placing the queen, we will mark it as cube, and where we are not placing a queen, we will just mark it with a dot. So let's first try to understand this problem with this given example of a 4 cross 4 board. The idea is we are trying to place 4 different queens on this board, and we will have to explore all the possibilities we could in order to generate the answer. Now this is going to be a very long video, so I'm just warning you beforehand. I don't want to take any shortcuts, and I want to make sure that I understand this problem and you understand this problem. So now let's get started. Basically, let's start one by one. Let's say that I put the first queen naively on this very first location. If I do that, which means essentially I'm eliminating all of these squares for any other queen to pursue and use it as for their configuration. Let's say I put this queen. Now in order to put the second queen, I have 2 options. So let's say randomly I just pick this option. Okay, so once again, after picking this option, also these squares are now being controlled by this queen. Next thing is, if I want to put another queen, there is no place for me to put the third queen, because this entire row has been covered because I put this queen over here. So let's try to revert that. Let me try to put this queen somewhere else. Okay, so let's say if I don't put this queen over here, then all of these squares would become empty. And once again, let me just try to put this queen on the second position and then try to see. So let's say if I put this queen over here, once again these squares gets controlled by this given queen, and now I only have one option in order to put the third queen. So I can put third queen over here, but that controls this option, which means once again I cannot put 4 queens over here. So once again I will have to go back, I exhausted all the possibilities for the second row, which means I still have to exhaust more possibilities at the first row by changing the position of this queen. So let's try to do that operation. For that I will have to clear the board and basically do a backtrack operation. Let's do that. And now I'm trying to place queen over here. Now which are the squares being controlled? Let me just quickly mark each one of these to make sure that I don't create any confusions. Now for the second row, I only have one possibility where I can place my queen. So let me do that, and let me also mark all the items that are being impacted by this queen. Okay, now for the third row, I only have one option. So let me also place one queen over here, and once again exhaust all the possibilities. And now for the fourth row, I only have one choice where I can place the queen, and that is this empty square. So now we can see in this case that we are able to place all 4 queens on a 4 cross 4 grid. So this is one of the potential solution. So we will actually have to mark this entire solution and place it inside our answer array. So the thing is, let's say that we create a list that is going to store all the answers. How we are going to take the snapshot of this is that we are actually going to create an array that is going to represent every single row for this given entire section, and for each of the row we are going to mark it as this, that we are going to store string values, where for the first two elements we don't have a queen, so we are going to mark them by dots, and then we do have a queen, so we are going to mark it by queen, and then we are once again going to mark it by dot. Once again we are going to do the same process, so queen and then dot dot dot. Once again for the next element repeat the same process, so basically 3 dots and then a queen, and for the last one we are going to dot queen and dot dot, so dot queen and dot dot. Okay, and so this becomes one of our answers. The thing is, this is not the whole answer, we could still have more potential answers. So let's say we explored one possibility, let's try to explore another possibility. And remember, once again we are doing the backtrack operation, going back to the very initial call. We already exhausted these two possibilities for the position of queen, so let's try to explore more paths. Let's say if queen is over here, then once again let's repeat the same operation. We are going to eliminate all the squares being controlled by this queen. The option is to place it over here. Once again eliminate all the options. Once again we can place a queen over here, and for the last one we can place a queen on this position. So once again this becomes another one of distinct answer, because notice the positioning of queens are different compared to our previous answer. So once again we are going to note this entire answer. Now don't worry, I will not put you through the painful process of going through the whole thing. Let's say that I just paste this answer over here as part of the next array list inside our answer, where we are going to return the list of array list. Okay, and now let's say we try to explore the very last option for the queens. Once again for the very last option we are going to be placing the queen over here. If we try to do this one, basically this solution would not work, because we would not be able to find appropriate queen positions in order to fill it out. So notice that in this case once again we filled out all these four possibilities because we placed a queen over here. If we don't do that, if we decide to place a queen over here, then once again we are eventually going to fill out all of these possibilities. So these are the only two distinct ways through which we can place all four queens on this 4x4 grid, and this is what we will have to return as part of the answer. So this is what is being asked us to solve. Now the thing is, let's see how we can actually solve this problem. So notice at the very beginning when I selected a queen over here, immediately I did not started rejecting this option. Basically what we can do is that at every single position we have two options to make, that whether we can place a queen over there or we can not place a queen over there. Now we will have to explore both the possibilities, and in this case we will proceed in column by column area. So we will try to put the queen on the first column. Based on that we will it will determine the position of the second column, and then third column, and then fourth column. So initially the idea is going to be that for the very first column on the leftmost portion or the very first value we will try to place queen. And let's say that after placing this queen, our logic would be that we will have to find an empty space in this particular section where the squares are not being hampered by this queen. We can completely ignore this entire column the moment we place queen at one of the position. So our jumping is going to be based on column by column level, and at every single column for all the n values we will have to determine that whether it is a sufficient place to place a queen. And the moment we find the very first opportunistic moment where we can actually place the queen, once again we are going to repeat the same operation for the next subsequent column, and once again we will try to find an appropriate cell where we can actually place the queen. So there could be two options. One option is that let's say that we are able to identify some place where if we just take a look at this example, basically in this example if I place a queen over here, we exhaust all the possibilities. Now there are no place for us to place a queen, which means immediately it should come to our brain and also in our program that placing queen over here is not a good idea. That is option number one. Option number two is that placing queen over here is not a good idea. So we are going to do the backtrack operation, and after backtracking we will first try to remediate our this mistake, and we would, instead of placing queen, we would place at the second possible place, and once again try to repeat the same operation. But eventually this will also not yield us the correct result, and eventually we would keep on backtracking to our very first decision. And through the very first decision, we would try to make sure that, okay, instead of placing the queen over here, let's try to explore other possibility. And then this would lead us to our correct result. So that is number one thing on we can understand that how we are actually able to find the answer. The logic is quite straightforward. We are simply going to do a recursive backtracking call in order to determine that whether the given path is a correct sensible path or not. But this is not as simple as it sounds, because there are a lot of computation and a lot of things we will have to understand and break down for our program to that how it is going to work. So let's quickly understand first that what is going to be the recursion we need to do in this case to complete the problem. Well, we know that for recursion we need two items. Number one item is that a base case, and second item is that we need a appropriate recursive function. Base case in this case is quite straightforward. The moment on the C4th column we find an appropriate location for the queen, we know that we already crossed all of these columns, and then we reach to the column 4 where we are able to find an empty slot for a queen to be put in. So which means this has to be the complete correct path that we are able to generate in order to fill the answer. And that is exactly what we are going to be storing as part of our base case. So what we will do is, number one, we will need some way to keep track of all the paths that we have taken so far, because by doing that we are doing two things. Number one thing is that when we do reach to that happy path scenario for our base case, we can actually add the path that we have stored for so long for the positions of queen as part of the one of the values for the answer. So that is number one thing. Number two thing is that using this path, let's say at some moment we decide that we cannot go further anyway, then once again we can just say that this path does not yield to the correct result. If it does not yield to the correct result, we can simply do a backtrack operation, and through the backtrack operation we will try to explore other paths. So just same way we saw over here that this queue location was not working out, so we tried to see for this queue location. Once again that didn't work out, so once again we updated from our queue location this one to this one, and then we try to identify that whether this is the correct path or not. So we made some judgment calls through our recursive function on what are the things we are trying to achieve. Basically, don't get confused. We are just doing exactly the same thing that I showed you on throughout the entire graph. The only difference is we are trying to do it recursively, and we are trying to follow both the things, that what is going to be the base case where we need to break out of the recursion and store the value to the answer. If we are not able to do that, then we will also have to do the recursion using the current path we are choosing in order to solve the problem. Now there are also few more things that we will have to understand. First thing is that at every given moment, whenever we are checking for potential candidates, we will have to understand that whether this path we are taking, if that is the correct path or not. Because let's say that in this case I place a queen over here, which means I am eliminating these elements that can ever be used for the potential queen. So now when I am at the column 2, I once again going to check all of these positions one by one, and in order to check that whether they are good candidates or bad candidates for my queen to be placed over here, I will need some method to basically do a validation that whether I can place my queen on this square or not. And the only way I can check is that is to check my current path that I have currently iterated over and see that this particular cell, has it being impacted by any of the queens that I have previously placed. And by doing that, we can actually make sure and find the potentially good values for our queen. So let's say that we identified potentially good values for our queen. So we did this operation for this first column. Then once again we repeated the same operation for this next column. Once again we are going to repeat the same operation for this third column. So logically we are just redoing the same thing that we have done in the past, but for the different input. And that's where the second requirement for our recursion comes into the place, because remember recursion needs two items. First one is a base case and second one is a recursive function. So as part of the recursive function, whenever we are moving to the new column, we are simply updating the value of the column, plus we are also updating the value of where we have stored the queen in the previous value inside our current path. So this will allow us to do the backtrack
and also allow us to move to the next value inside the logical iteration of our recursion. On top of it, that's why this is a hard problem, because there are a lot of on top of it that you will have to understand. At every given moment, once we reach to the very end, in the current path we are not keeping track of all the items of the board. We are just simply keeping track of the position of queen that we have placed so far in each of the columns. So once again we will have to have a method where we are actually generating the board based on the positioning of the queen. So remember that ugly board that we are seeing, like that contains dot q dot dot, then once again like dot 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 q, and this type of like Morse code type of structure. We will also need a method to generate this as well. And this is the solution. Basically this is the optimal solution in order to solve this problem. We are using backtracking, we are using recursion. For recursion we have a base case, we have a recursive function, we are keeping track of the current path we are at. We need to have a method to check that whether the given path is valid or not, to place the queen based on the previous queens we have placed. Plus we will need a method to generate the board that we need to generate in order to solve the problem. And in the end we need to store everything in an answer, where in the answer we are actually storing the bunch of different arrays as part of the array. So it's going to be an array list that contains multiple array list. And if we see, if we try to calculate time and space complexity in this case, well, it's really difficult to calculate the time complexity, but let's try to understand the time complexity logic in this case. If you can understand this, then your logic to solve time complexity is going to be pretty beautiful. Logic is quite straightforward, that for every single column we are iterating over all of these values, and we are doing it for each of the columns, which means basically we are in the worst case scenario, we are iterating over each one of the elements. So basically and the number of elements we know are n to the power 2, and at every single element we have two choices to make, whether to include that element or not to include that element, which means we are actually doing 2 to the power of n multiplied by n, or 2 to the power of n square work uh, for this one. And we will have to repeat the same operation for each of the columns, because remember that in column 1 there are 4 possibilities that can lead us to different paths, which means we will have to calculate this for each one of them. So we will also have to do this operation n times. So time complexity is horrendously bad, and that's why if you read the problem statement on lead code, we are only being told that the value of n can only be between 1 and 9, nothing more than that. We are dealing with a very small number of finite solutions, because if you try to do this with million values, we need quantum computers in order to solve this problem. Okay, now let's quickly see the coding solution, and I hope my solution made sense to you.
Okay, so the very first thing we are doing is that we only have value n that we need to return. So first of all, we are creating a blank board of n cross n size, and we are marking all the values as initially as dots, because we don't have any queens placed at the moment. We are also initializing a new array list of list called result, where we are going to be storing all the result, and then we are going to be calling our backtrack method. This backtrack method is going to do the backtracking and also recursive function for us. In the input we are providing the new board that we just created, plus the starting index of the very first value that we need to iterate over, and the result array list that we have just created in order to store all the answers. Now let's understand our backtrack method. So very first thing we are doing is, this is our base case, that if the current length of our column is equal to the length of the board, which means we have placed the queens correctly on all 4 columns or all n columns. So the correct current path or the current version of board is suitable enough for us to place it into the result. But the thing is, we are not directly placing it into the result. We are actually calling a construct method to construct the board we want in the subsequent manner. And first let's just see the construct method. Okay, so in the construct method we are just passing in the board. On top of it we are checking that what are all the current positions of the queen that we currently have, and we are just adding those values as part of the queue. Apart from that, we are not doing anything else, and we are simply returning that to the result. Okay. Next thing is, so let's say we add the appropriate result over here. Then we have our for loop, which allows us to iterate over all the values inside our given input, where we are starting the value from 0. We are going until the length of the board, and we are just doing I plus plus. Very beginning, for every single board position, we are checking that is it a valid place where I can place my queen. And this is valid method is doing nothing but checking that based on the previous paths that we have calculated, whether we have any particular queue or any particular queen placed before, that is either in the row of that particular queue, in the column of that particular queue, or in the diagonal of that particular queue. If that is the case, we simply need to return false, that this is not a valid position where we can store our queen. If none of these cases are true, then only we will return true, saying that yes, this is a valid place where we can actually place our queen. So once we find a valid place, we update the position of our board to mark that value as q or queen. And then once again, so this is what this we are updating the current path. And then once again, we are going to be calling our current recursive method with the new recursive call, where we already updated the current path of the board. And we also call in with the next index position or the next column we will have to iterate over, and we will keep on repeating the same process. Once we receive a call back from our board, we will also have to explore other paths that we haven't explored so far. And that's where this recursive call comes in, where remember, first we are marking this current position as q, but next we are marking this current position as a dot, that this is no longer a q, and we are exploring other paths. And this is the whole solution. Now let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs 87% faster than all the other solutions, which is pretty good, comparing that how difficult question this one has been. Also in terms of memory usage, our code is pretty good, and in terms of like much better than a lot of the other solutions. Once again, the solution of this code is present on our GitHub repository. I highly urge you to go and check it out and try to solve this problem. If you can solve this problem, I don't think any backtracking problem would be a cause of concern for you. Okay, thank you.